Hi, everyone. So today I said I would do a Q&A about kind of the backstory and of our physics project and kind of questions about how we're doing the project and how things we hope will work going forward. It looks like I have a bunch of questions. Gosh. Those are kind of weird questions. What are decisions that led me to do this as an open science project? Well, it's a kind of a long story. I mean, this project is kind of the outgrowth of ideas that I had about 30 years ago that I developed and wrote about in my big book, New Kind of Science. I spent about 100 pages writing about them there. I put a lot of effort into making those pages be something that would be readily understandable to a wide range of people. I think I succeeded in the sense that lots of people seem to understand them, with the probable exception of some of the sort of hardcore physics folks, many of them friends of mine from when I worked in physics many years earlier. I think that in a sense, it was one of these cases where the very act of making something easy to understand made people who expect things not to be easy to understand think there wasn't anything to understand, which was sort of a shame. And then, you know, that book came out in 2002, and I put some effort into working on kind of the follow-up to the physics side of it. I should explain that in that book, the main point of that book is kind of the discussion of kind of this new approach to thinking about things computationally rather than in terms of things like mathematical equations. And the thing that's been really, frankly, spectacular is that over the last, I don't know, 15 or so years, what had been a 300-year run of people sort of making models for things in terms of mathematical equations has transitions, and I'm not the only contributor to this, but I think the book was an important catalyst for that process. Things have transitioned to the point where most new models that get made of things are made in terms of programs, not in terms of mathematical equations. It's kind of a silent but very significant revolution that's happened in science. And I'm kind of, I kind of said in the preface to that book that you know, what was going to happen was this would inexorably happen. And while people might say, oh my gosh, this couldn't possibly happen when it's first discussed, as it was in the book, you know, in time, people would say, well, of course, this is what has to happen. It's totally obvious. And that's pretty much what's happened. But, you know, one area where this kind of computational approach to thinking about things didn't take root is in fundamental physics. And sort of try as I might, and I didn't try that hard, to kind of kind of pound it into people. Yes, this is a worthwhile thing to try. Not a lot happened in that area. And so I was, well, it's kind of a long story. I tried to tell this story in the long backstory post that I wrote last week. I mean, it's a long story, and the Max Piskanoff and Jonathan Gorard were students at our summer school, which was kind of a thing that we invented to try and sort of stimulate work related to new kind of science and later other technology of ours. That's something we started back in 2003, and we probably had 1,000 people go through our summer school, and lots of really interesting people who've done really interesting things. But two of those people were Max and Jonathan back in previous years, and that's kind of how they got involved in this project. And they're the ones who kind of really encouraged me last year, we got to do this project. And so I said, okay, if you guys come and help, then let's go do this project. Now, this question of how do you do a project like this? You know, what I did in the case of the New Kind of Science book, I started working on that book in 1991. And you know, at the beginning, I was like, okay, I'm going to talk to people about this and so on. But every person I talked to, they said, well, what about this? Did you think about that? What about this? And they were reasonable questions, not bad questions. But the problem was, you know, how was I going to get this project done in finite time? I thought it might take a couple of years. Actually, it took more than 10 years to do that project, because I really was trying to as perfectly as possible, explore the things I wanted to explore. And it worked great. I'm very pleased with the way that the New Kind of Science book came out. I use the online version every day. It's kind of a good condensation of things I have ever known. In fact, I'm constantly finding things that I didn't know I knew. Just last night I was working on actually the index for the finishing off the index for the book related to our physics project, and it has we're reprinting some pieces of the New Kind of Science book, and I was like, really? Did I actually talk about that stuff in the NKS book? I didn't, because I was so busily pushing to finish the work I was doing. I didn't go back to look at what I'd actually said, but it's like, oh, that's kind of interesting. I forgot that I talked about rotating space-times and things in NKS. But so I was pretty pleased with the sort of completeness and in a sense perfectionism of NKS, but it took 10 years. And in the end, I kind of shut out all external stimuli because I knew that there was no way I could get this done sort of in my lifetime, so to speak. I just noticed an article about my friend Don Knuth, who's been working on his series of books since the early 1960s. And I kind of, I feel for his situation of having spent basically a lifetime working on that piece of scholarship. And that's an easy thing to fall into when there's a certain set of things that are possible to do and one can go explore them. So one of the issues with this physics project is, at first I thought it was going to be much harder than it's actually turned out to be. At first I thought we would not make that much progress. It will be quite glacial. And I was then imagining that, we would pick away at it over the course of decades, as different things get figured out. As it turned out, we sort of accelerated rapidly and figured out a lot more than I expected we'd be able to figure out. But one of the things I wanted to not do was to make the mistake that I made with NKS, which was to basically try and figure out everything and spend a decade doing that. I wanted to kind of get it out there and let other people contribute to it, not least because I think it's a lot of fun. And I think it'll be really cool for a lot of other people to have fun working on this as well. I mean, there's lots to do in sort of figuring out fundamental physics. I think it's really kind of exciting what's happened, and it's a great thing for people to share the fun. Plus, I think it'll get done better that way, and I think it's something where integrating it with what else is being done out there in the world in physics is really worthwhile. It's turned out to be much more worthwhile than I expected, in the sense that it's something where I thought we would build a sort of separate prong for how physics works, different from the kinds of things that have arisen in existing mathematical physics. As it's turned out, it's sort of a beautiful merger of a new set of foundational ideas together with a lot of methodology that I think there's still much more to work out from existing mathematical physics. All right, let me take a look. Can the average person contribute to this project? If so, how? Well, certainly the average mathematician or physicist can absolutely contribute to this project. And I would say the number one thing to do early is take whatever methodology you know. If you know conformal field theory, if you know the twistor theory, if you know something about geometric group theory, whatever, take some existing thing you know and see how to use the methods from whatever you know, and see whether you can use them to understand more about this kind of model that we have. I think one thing that's really cool is how richly it's possible to use a whole bunch of different kinds of existing methods on these kinds of models. That is, these models are very general things, and there's a lot of depth to what one can say about them. And pick an area. We can do that. If people want to suggest things on the live stream, I can try and suggest how some particular area of mathematics or physics might relate to these models. Same is true with computer science, particularly theoretical computer science, particularly some of these things like geometric computational complexity theory, theory of distributed computing. These are both areas where I think there are really, really interesting things that can be done by using, we'll talk about tomorrow actually, talking about using ideas from distributed computing to apply to physics, and some of the ideas from physics to apply to distributed computing. And I think that's, again, something that's likely to happen is as one uses methods from some particular area to try to analyze these models of fundamental physics, that will make suggestions for other things one can do within those areas. And I think that's going to be really fertile. So that's in terms of the professional, so to speak. In terms of on the computational side, there's a lot of really cool and interesting things that we certainly need help with. I know one of the early things is parallelization and GPUization of the actual simulations that we have. Another is figuring out how to do these things with virtual reality and so on in a good way, so that we can really explore these hypergraphs in a more experiential way. That's something I'm keen to see. I think there's a lot of sort of practical computational kinds of things. I would say also figuring out, and this is more difficult, the first set of things I mentioned are things where we sort of have a pattern for what to do, and it's a question of doing great software engineering to really, and great kind of algorithm invention to really have them work well. There are other kinds of things that involve more analysis types of things. Those are a little bit more scientifically challenging, I would say, but there are also places where people can contribute. Now, having said all of that, for the person who is, less the professional physics, math, theory of computing type person, well, first thing I want to say is we're going to be doing our summer school, which we've been doing for 17 years now, physically. For the first time ever, we get to do it virtually this year. And we will be having a physics track, fundamental physics track at the summer school. In fact, we'll also have, it's a 3-week program that's mostly about people doing original projects. We're going to add a week 0 for physics, which will be more of an introduction to this project and things we know, that will be more oriented towards just the exposition, the education about this project, and encourage people to come to that. And if you want to apply to the real summer school, please do that. We should have good capacity this year because we're doing it virtually, and it's really a great place to sort of get launched. I would say that it's appropriate. The fundamental physics track will be particularly appropriate to people who are graduate students in relevant areas. I think also somewhat more advanced undergraduates, it's a possibility as well. The rest of the summer school will not kind of require sort of physics knowledge, and I encourage people to get involved with that too. Now, having said all those things, if you're somebody who doesn't have sort of formal training in physics, math, theory of computing, those kinds of things, how to get involved. I think the most interesting thing is exploring the kinds of underlying models that we've discussed in this project, and that are the inspiration for this project. Even things like cellular automata, things like substitution systems, and so on. What made this project possible is the fact that we have intuition about how those other kinds of systems work. And in fact, even within my big paper about this project, there's a big chunk of it that's about string substitution systems being used as kind of an idealized model of our full hypergraph rewriting system. So I think there's one of the things that's really great about this area of sort of exploring the computational universe is that nobody's done it before. So if you're somebody who is sort of intellectually organized and you can sort of deal with some Wolfram language programming, but not much, I suspect, this is something where you can explore these different areas. So for example, there will be plenty of things to explore about, let's say, string substitution systems, about some of these hypergraph systems, or even about cellular automata, where it's a question of understanding sort of the fundamental science of how these things work. It's kind of the analog of pure mathematics, but directed towards the computational universe rather than towards sort of traditional mathematical ideas. And that's something where there's a pretty decent blueprint for how to do that kind of science that, my big new kind of science book talks about. There's lots of work that's been done by people. We have a journal called Complex Systems that we've been publishing since 1986 that publishes a bunch of papers in these kinds of areas. And I think that that's what I would suggest to people who are interested in sort of getting involved in science, maybe don't have a particularly elaborate formal background in some area like physics, for example. Go start doing experiments. Don't expect that the experiments you're going to do will discover the electron, so to speak. That's not the point. The point is to explore the intuition for, let's say, how do causal graphs work for cellular automata? We don't know. We started looking at that. We spent 15 minutes looking at it. It's clear that it's really quite interesting. It's clear that it doesn't require sophisticated mathematics to understand something about it. There's, first of all, just the empirical exploration that has to be done. And I think that's a really worthwhile thing for people to do. Let's see, we have a lot of questions here. So I am going to try and, there's a bunch of questions about peer review. How long will the project take? Who knows? I didn't make the universe, I think that, here's what I think. I think that assuming that it gets done with reasonable intensity, the question of how what we've done relates to existing mathematical physics, that's a couple of years for that to be explored, I think. Now, in terms of when do we get to find the electron and find the muon and so on, we don't know. I think there is a decent chance that that could happen in a matter of months. It could also take decades. I don't know for sure. And that's, I think that this whole project, if you say, is it obvious that this project would happen in the year 2020? The answer is, it's not obvious at all. I mean, this project, I'm sort of embarrassed that I didn't do this project back in the 1990s. But I also think that if we hadn't done this project now, this project wouldn't have been done for a very long time. And so, there's partly the question of what gets done depends on people actually trying to do it. And that's an important piece to this whole story. I'm gonna take, there was some original questions here, but which are perfectly interesting, but I'm gonna go to some more real-time questions here. Let's see. Well, we're asking questions about why do this project live, because I think it's interesting for people, and because it does not diminish what we would do, and it enhances it. And so why not do it that way? Part of the model for this has been the live stream design reviews that we've been doing for the past year and a half or so for our company. I mean, I realized ages ago, we do all these things thinking about, how are we going to implement, I don't know, some kind of time series or some kind of functional programming construct or something in Wolfram language. And I realized, these are really interesting intellectual discussions. And so I thought, gosh, it would be nice to expose people to these. That was my first thought, is just people would just find these interesting, and it's not going to make any difference to the way that we're doing these discussions. We've been a geo-distributed company for ages. We were always doing these discussions through, Zoom and such like. So let's just let some other people be in on the fun, so to speak. But actually something else happened, which was that the people who started tuning into those discussions started being really helpful. And it's, if you're doing design of a piece of technology, there are both problems that come up, and it's like, what do we do about this? What do people think? Somebody on the live stream will say, well, what about this? And by golly, it's a good suggestion. And we just saved, many hours of work because somebody was there who was interested and who had some expertise and was able to contribute. I think it's also been, for some of the things we're doing, it's really cool to have sort of an instant focus group of what do people really think about this. And even this question of, here's the thing we're thinking about building in our language, does anybody understand this? And if the answer is nobody understands it, it's a bad thing to build. So that was sort of the thing that's led me to think that this is a good thing to do, is that we really had a great experience. And I think it's really helped our design process for our language and so on, to have exposed it on live streams. And my theory was, let's do that for physics. Let's see if we can there's a lot of expertise out there about physics and mathematics and related things and computational side of things, and let's let people let's get that involved in what we're doing. And when we discuss, I think we're still sort of ramping up to the full point where that will be as effective as it can be. But I'm fully expecting that in time we'll be doing sort of totally technical discussions that will have really great specific answers. I mean, I think one of the things that I've really found neat in our live stream design reviews is people literally just sending through code fragments saying, hey, this is a possible way this could work. Here's a code fragment, and we bring it up on the screen and we run it. And it's like, okay, now we can understand it. Thank you. And that's what I'm hoping we'll be able to do with physics as well. Let's see. So will there be journal publications of the project, and will there be open access so there are no paywalls? That's a good question. I mean, the fact is we're putting everything we're doing out on our website. We're also submitting these things to standard, journal type places. And I think, there'll always be a version on our website. I don't know what the value sometimes of I think journals are partly, well, maybe we'll get some peer reviewers to put free work into going through 450 pages of documents. I think we're going to see people doing that, not because some journal said, can you peer review this, but because they're interested, which is a much better reason, frankly. And I also think that, so it's a good question, and a good issue for us is to make sure that doesn't happen. I mean, I think this is a project, sometimes a lot of projects that get done in basic science, it's like, who pays for these projects? How does this work? And usually, the basic principle is governments typically pay for basic science projects, and it's kind of it's one of the principles of basic science. Why does basic science happen? Why do people do basic science? In whose interest is it to pay for basic science? And I think that what we have here is a somewhat anomalous situation, which is that I have enough resources because of the fact that we've thankfully had a successful company for 30 years to be able to do a project like this without really worrying about the micro details of how much does it cost to put up the website and things like this. It's going forward as we scale the project up. It can't all be my funding, so to speak. If indeed we scale it up as an organized thing, as I think we want to, and we think it's a worthwhile thing to do. Now, in terms of we're in a somewhat anomalous situation because this wasn't paid for by the National Science Foundation grant. Had we sent in an NSF proposal saying we're going to study the fundamental theory of physics, I can tell you with absolute certainty that it would have been rejected. And we would be saying, oh, we can't do this because nobody's paying for it and so on. It's not the nature of a large institutionalized field to be able to deal with kind of big, let's rethink it a bit type stories. And I don't think that's bad. I think that's just a feature of what happens when you have tens of thousands of people working in an area. You have to have a certain structure. You have to have a certain institutional structure to sort of keep the thing organized. And that kind of structure isn't particularly conducive to making kind of the big jumps forward, so to speak. It's something, when you have a young field before it's been institutionalized like that, then you get to make the big jumps forward. And the thing that's really cool with this project is we are at the big jump forward stage, and not just for things that we're doing ourselves, for other people too. I mean, I've seen this in a bunch of fields, probably a dozen fields in the course of my career, where there's some methodological or conceptual advance, and then suddenly, for a period of years, there's a lot of low-hanging fruit to be picked. We are in the low-hanging fruit period for this approach to fundamental physics, and I think it's really neat. I mean, we haven't been in a low-hanging fruit period for fundamental physics for a very, very long time. I mean, it last happened probably in the 1970s, as a time when I was involved in particle physics, where I was one of the fruit pickers, so to speak, of being able to take ideas and methods that other people had invented and being able to do interesting calculations and figure out things that seem to have survived as interesting because I was in an environment where there was a lot of low-hanging fruit that was provided. And through, I would say, really good luck with this project, we are at a point where there's a lot of good low-hanging fruit. And I look forward to picking some of it, but frankly, I really look forward to seeing other people have fun picking other parts of it. And I hope people will be able to do that. So there's a question here from Lizard Liz Arden, I don't know, or maybe Liz Arden, I don't know. It's very hard to parse these handles. At what point when you started working on this did you realize it was worth investing decades in it? So look, here's the story. I started working on kind of simple programs out there in the computational universe and what they do. I started working on those things in about 1981. I'd been working in particle physics, and I'd also built my first large computer system at that time. And I kind of, for various reasons, wanted to have some fun, and I wanted to see whether I could do something that would be kind of a slightly slightly kind of a thing that would just be sort of easy to do. I also was fortunate enough. A piece of personal history. I happened to have just won one of these MacArthur fellowships in the first batch of those things, actually. And as the youngest person, having got one in that first batch, that caused a bunch of kind of undue media interest, I would say, at the time. But that was that was one of the contributors to me just sort of saying, look, let me try and do something fundamental and fun, and not kind of part of the mainstream of the hard work of doing, let's say, particle physics. And so then I got interested in, okay, let me just explore these simple programs and what they do. And actually, it's rather easy to do these computer experiments. And then I started doing them. And then I said, this is really interesting. And then I spent several years kind of working through the consequences of those computer experiments and trying to sort of roll up the big guns that I knew from physics and mathematics and computer science to analyze what was going on there. And I kind of finished that process around 1986. And then I started saying, okay, this was take one of my sort of organize a science idea. I was really interested in the point that you could have very simple rules, and yet the behavior you would get would be very complex. And so I thought that's a really interesting phenomenon. It's a very general phenomenon. There's a lot to study with it. There's a lot of applications of that phenomenon. Let me try and sort of stand up a science around that phenomenon. And so I called it complex systems theory. I kind of was avoiding the term complexity theory because that's sort of already been taken by computational complexity theory, which is something quite different. But so I started talking about complex systems research. What could one do with it? I remember, actually was recently reminded of this, the Santa Fe Institute. It's a small research institute. I was sort of at their founding meeting where it was like, well, what are we going to concentrate on at this thing? And I'm like, I've got an idea. This complex systems theory thing is a good idea. And that ended up happening there, which was really nice. But this was around 1984, 1986. I was really like in the mode of, there's this really interesting direction in science about studying complex systems. This is a great thing for people to do. Let's go do it. Well, it worked out only so-so. I started a journal, Complex Systems, still thriving today. I tried to sort of, the many sort of manifestos that I wrote for why complex systems research would be a good thing to do. And I sort of sent that out to people. I was a pretty, I would say I was I was still fairly young, but I was like 25, 26 years old then. But I was sort of pretty established in science and pretty well known in science. And so I was, I had a good platform to kind of present this kind of complex systems theory idea. But frankly, it didn't go very far in terms of other people doing it. It was like, people at the National Science Foundation, the main US sort of basic science funding thing, were like, well, we have a physics program, we have this program, we have that program. Does it fit into those programs? I said, well, no, actually, it's a new kind of thing. It doesn't really fit into those programs. I remember one day, I remember a big sort of discussion with a large US funding agency about, well, we got all this money for studying the space plane. Does it fit into the space plane? Not really. I mean, it happens that we can do some things with fluid dynamics using these methods, but that's a corner of the main science which should get studied. So there just wasn't really a mechanism for sort of having a big initiative around that kind of science at that time. Now, actually, subsequently, well, okay, so that was in mid-1980s. And so I actually, from a personal point of view, I went around, I tried to start a sort of good research center for doing this kind of science. I talked to sort of many of the major universities in the US. In the end, University of Illinois was the one that sort of came through with the best proposal for how we would do this. And to give them due credit, they lived up to the things that they said they would do. And I think that was it was a good relationship there. And I brought in a bunch of new faculty members and so on to be part of this Center for Complex Systems Research that I was building. But I quickly realized that it was, for me personally, a pretty lousy way to actually get things done, because I was not totally incapable of organizing things, and the fact that I've been a CEO now for more than half my life, and that we managed to do some interesting things with our company, is probably a sign that I don't get a total fail on the organizing things to have happen. But I would say that organizing sort of a research center within a university is probably a poor use of my skills. It's sort of like raise money for other people to do research. That's not kind of what I'm interested in doing. I'm more like, I like actually creating ideas and turning them into real things and so on, rather than doing kind of the sort of the promotion of other people's work to do that, so to speak. So in 1986, actually, right after we kind of got the Center for Complex Systems Research started, I said, okay, let me understand whether there's another way to do this. And I realized, well, actually, I need better tools. I built this thing called SMP, which was kind of a forerunner of Mathematica, but I needed better, sleeker tools. Oh, and by the way, there is a commercial opportunity because PCs were just getting to the point, or personal computers, at least not yet IBM-like PCs, but personal computers were just getting to the point where they could run sort of sophisticated software. And so I was like, not only do I need this tool, but also lots of other people will be able to use this tool too. And that will allow me to create an environment where it's possible to do the things that I want to do. So we started building our company, Wolfram Research, back in 1986. And the thing that by mid-1988, we released the first version of Mathematica. That went really well. By about the early part of 1991, I was in this interesting position. The company probably had, I don't know, 150 employees or something by then. And I had a gazillion ideas for what we should be doing. And I realized I am feeding ideas into this company far faster than something of the size that this company has, or the structure that the company has, can possibly absorb them. And actually, I have to say, along those lines, I of course kept my 1991 to-do list, and about maybe 3-4 years ago, we finally finished my 1991 to-do list. So it was, but I decided back in 1991, I decided, look, I can be spending all my effort putting ideas into the company, but it just can't absorb them at the appropriate rate. And so let me go to what I was originally planning, which was use the tools and the environment that I've created to do some things that I'm interested in doing myself, which had to do with doing basic science and sort of exploring more about this kind of, how does complexity arise? What's the sort of science around complexity? And so that got me started I became a remote CEO, and I started working on basic science. What happened was I discovered a lot more than I expected to discover, and that's how I ended up spending 10 years working on this book, New Kind of Science. But what I learned, so during that period of time, a couple of things happened. So somewhere in the mid-90s, finally, the complexity thing started getting government funding and things. And it happened in a really bizarre way. It happened as a piece of kind of interest in environmental research and so on. It was really unpredictable what was going to happen. And it got some, it got actually quite substantial sort of interest in kind of the science establishment. I would say that I had made what I consider to be a bad mistake in terms of the setup of the field, which was, if you look at mathematics, mathematics has pure mathematics and it has applications of mathematics. And they're sort of separate. I mean, people do pure mathematics with various justifications for it's aesthetically interesting, it's it's a great human activity and so on, and they just do it for its own sake, as a thing by itself. And then there are all the applications of mathematics, which are done often in the fields in which they are applied. I mean, there's this kind of applied mathematics is kind of this funny area that's gradually morphed over the years and means different things in different places and so on. It's kind of a funny interface layer between sort of the pure mathematics and the applications of mathematics in different fields. And I think that what I failed to do in sort of the complexity area is really insist there's got to be a pure field here. There's got to be a field that is just about the abstract investigation of simple programs and what they do, having nothing to do with the applications. Because what instead happens is that you say, well, really, I'm trying to study some feature of biological evolution. So I'm going to kind of morph my model. It's not going to stay simple. It's not going to stay something where I can really explore the model for its own sake. It's going to wind up being something where I've got, things related to, fish turning into amphibians and so on, which is not something that is going to be a core thing about the model. I want to make one point here, which has really been emerging with our physics project, which is the model that we're using for the physics project is a very general minimalist model. So what happened with cellular automata are also a very general minimalist model, particularly the kind of one-dimensional ones that I kind of made up back in 1981. And it's literally been the case that there are 256 of these elementary cellular automaton rules. And I used to have a file cabinet where I would literally put papers that were applications of Rule 18, applications of Rule 22, applications of Rule 184, and so on. And gradually, almost all these rules found applications, whether it's in road traffic flow, whether it's in studying, the stomata on leaves, whether it's in studying, patterns on lizards, whether it's in doing different kinds of things. And the lesson from that is any sufficiently minimal model will get applications, and they will be very diverse. And having a core understanding of the model will allow you to make conclusions about a lot of different applications. So that's what happened with cellular automata, has happened with cellular automata. Okay, one thing that I've been really excited about with our models about physics is I've realized actually just in the last week or two, my gosh, these models are applicable to lots of other things too. I mean, the first thing I started realizing as I was studying epidemiology in the face of this pandemic is that, the geodesic balls that we're constructing in our hypergraphs are very related to the contagion networks in human contact networks. And then we started realizing that the way that you reconstruct space-time from kind of the interaction of world lines is the thing that you need to understand for enhancing digital contact tracing for people and cell phones. And then I started realizing that a bunch of the stuff we're doing is extremely relevant to distributed computing, that there are sort of general questions about distributed computing that are really directly addressed by, one of the things, we'll probably talk about it tomorrow, is one of my new ideas is something that I might be able to solve, something I've thought about for 40 years and never been able to solve, about sort of evaluation orders and asynchronous computation in evaluating expressions and things like combinators and so on. And I think there's a notion of using reference frames and to be starting to talk about, you're doing distributed computing, you are essentially programming in a certain reference frame. And I think that's going to be an important concept that we're going to be able to explore. And the exploration of that is sort of informed by and supported by these models that we made up for physics. But because they're so minimal, because they're such minimal models, they have broader application. I think also, and here's a weird thing, I think they may actually give us a nice way to think about a model for evolution, for biological evolution. Not at all what they were intended for. I built these models because I'm interested in fundamental physics, but by kind of drilling down to get to the point where one has the most minimal model, which I think has been important for physics, we're getting something that's also important for other applications. Maybe we'll talk about that some other time. I think that there's a way of thinking about kind of the multi-way graph as a way of representing kind of evolution paths and a way of thinking about branchial space and causal disconnection and speciation and so on. It's all very, it's in a sense very weird, but it's a lesson to some extent that we should have learned from mathematics, that sufficiently core pure mathematics, let's say calculus, for example, ends up getting applied in lots of different places. And it's going to be the same kind of thing here, I think. but in any case, that was a long answer. I can't even remember now what the question was. But to the issue of so one of my experiences in kind of trying to sort of stand up a science was with the sort of science of complexity, and I think I made some mistakes there. I think in particular the failure to really carve off this kind of what I would now consider sort of a new kind of science that is about the science of the computational universe, carve off the pure science part of that is a mistake. And I think now we actually have, from this physics project, potentially an opportunity to redo that. Actually, I'm really interested. People can come up with a fantastic name for this new kind of science that's about studying the space of possible rules, the computational universe, and so on. I have spent years trying to come up with the great name for that field, and I've never really succeeded. And I think that would be a quite helpful thing. And so people have suggestions. I'd love to hear them. I've got my Latin and Greek dictionaries are well thumbed for trying to find good things. And unfortunately, almost all the words that you might think you would use, like things that with roots like log for logos and things like that, or arc for logos for word, archos, archos. I'm forgetting my Greek for rule or law. These are deeply used for logistics, logic, etc. Architecture, archetype. These roots have been used many places. So those roots aren't really so useful, I think. But anyway, I digress. But that's so the thing that I'm sort of hoping here is one of the things that was difficult for building up sort of the new kind of science around the computational universe is it didn't really have a home. There wasn't an existing field that and by its nature, and that's sort of why I called the book A New Kind of Science, because that's what I view it as being, and that's what one has to think of it as. If one says, well, it's actually a piece of mathematics, well, no, it's not. Its methodology is quite different. Well, it's actually a piece of computer science. Well, no, it's not. Its methodology is quite different. But for this physics project, the methodology actually is something we already know. It's the methodology of physics and mathematics and theoretical computer science and so on. These are the methodology, the ideas, the foundations are a bit different, but the methodology is actually an existing methodology. And I think that will help in terms of I hope, in terms of planting this project within the existing enterprise of kind of intellectual development. Now, it has to be said that the question of how do you inject kind of a sort of a change in the sort of conceptual foundations into a field that is comparatively mature, as for example physics is. Well, that's a challenging thing, and I don't know what the best way to do that is, and maybe what I'm trying to do here and with the openness of this project is in part to solve that problem, because I don't know how to solve that problem. I mean, I was just having fun. I sent my my big paper about this into the arXiv preprint server. I'd never sent something into the arXiv preprint server before because I'd known Paul Ginsburg, who created the arXiv preprint server, since long before he created that. But I wasn't doing physics or writing papers, academic papers, by the time he'd created arXiv. So I've never sent anything in there. So I asked Paul, what's involved in sending something in there? And he wrote back to me and said, 100,000 people have figured this out. You'll be able to figure it out. So, and he gave me some other hints, but so I figured it out. But it did take. I was kind of interested. It took about a week to get. I mean, admittedly, it's a big document, a 450-page document. But I was saying to Paul, I was kind of hoping that he had a filter for arXiv where any paper that claimed to be a fundamental theory of physics would be summarily rejected. On the grounds that there hadn't been any paper that could validly claim that for 100 years. So it's a good sort of Bayesian assumption that any such paper will be crazy. But he said, no, that wasn't true. So that's a pity, because I was hoping I was going to be able to tell that story. But actually, I think it was just the thing was a big document. And so it takes a while to go through their processing system. Okay. Oh, yeah, I'm sorry. The question was how did I... why did I want to, why did I decide to invest decades in doing this? Well, I think the main thing is the exploration of the computational universe is something I just realized there's just an amazing amount of stuff to do here. And the thing that's been sort of really interesting in my life and partially intentional and partially not, is that I've sort of alternated between doing basic science and doing technology. And it's actually, I didn't do this on purpose, really, kind of. But, I started off doing particle physics. That led me into doing computation and building my first computer language. Building my first computer language led me to kind of think about how can we use computation as a foundation for making models of things, led me into cellular automata and things like that. That, in turn, kind of led me to want to make tools like Mathematica and so on. Having made those tools, I then sort of got launched in this whole new kind of science direction. One of the consequences of that new kind of science direction was that I realized that there sort of wasn't a bright line between the intelligent and the merely computational. And that sort of unlocked for me something that I wanted to do since I was a kid, which was to build kind of what I would now call a computational knowledge engine. And that's how we came to build Wolfram Alpha, was a result of sort of the philosophy of NKS led to Wolfram Alpha. And then from Wolfram Alpha kind of led to Wolfram Language, and led me to kind of think about sort of the foundations of AI, and to really understand this phenomenon of sort of, we have computation over on one side and we have kind of human thinking on the other side, and sort of how do we make this bridge between computation and human thinking, and a lot of kind of foundational stuff about computational language and about sort of AI ethics and all kinds of things like that. Actually, none of those things fully prepared me for the physics project. The physics project was something that I've been sort of wondering about on the side for a long time. I would say that, I started working on it in the 1990s. By the mid-1990s, I had many of the ideas that we now see in this project. And as I say, I put them into the New Kind of Science book as sort of a use case for this new kind of science, more so than a central point of the book. It was more like, this is a use case. I think that then I failed to follow up as much as I should have done. And part of the reason, I won't make too many excuses, because I could certainly have done it. But when New Kind of Science book came out, it's a feature of new paradigms that pitchforks come out along with new paradigms. And what I realized actually only very recently, as I was going back and looking at this history, there were many areas where people were very interested and very immediately absorbing the ideas in New Kind of Science. But the one area where there was kind of a lot of resistance was in fundamental physics. And that was particularly strange to me because, I'd been in that business. I knew all these people. And, it was strange to me that they would say, oh, this all has to be irrelevant. There's nothing interesting for us here. I've been in that field. I've been somebody working on doing things that I think people thought were fairly interesting in their field. And it seemed surprising that it was like, nope, this is too alien. We don't want to have anything to do with this type thing. And I have to say that put me off, because basically my thinking was, if I'm going to do a project about sort of technical fundamental physics, the primary market for that project is the technical fundamental physics people. And if they don't want this project done, why am I doing this project? I mean, for me, the project of understanding kind of the computational universe, it's a more general project than physics, or at least it seemed that way to me, in the sense that the computational universe, our physical universe, is just one little data point, one little point out in the computational universe of all possible universes. I actually came to realize only a couple of months ago that I wasn't quite right about that. But that's a different story. But at least my thinking back in the early 2000s was that this sort of exploring what was possible in computational language, started building Wolfram Alpha, things like this. These were really super interesting projects that the specific case of fundamental physics, that was interesting, but its target market didn't seem to want it. And so it's like, let me go work on things where I think they're really deep and interesting and intellectually rewarding. And by the way, it's kind of nice that people actually seem to like them. I suppose I got spoiled because I've been building tools for a long time, including tools that get used a lot by physicists, among many others. And tool building is a very is generally it's a thanked operation. It's something where people are like, thank you for giving me these tools, and that's really nice to hear. I sometimes think language design is a bit more thankless, because basically you put all this effort into language design, you finally figure out, we finally figured out this really good way to do something, and then everybody who sees it thinks it's obvious. And the only time when you ever hear from people is when you made a mistake, and when the thing has some ugly little imperfection and doesn't work in a clean way. So I don't really, I mean, language design as an intellectual activity is my top intellectual activity. It's the most interesting, it's the most kind of pure sort of thought to actuality path that I know. And it's something that I personally am very, very happy that I've been able to spend a large part of my life working on language design. I think it's a very pure form of expression of intellectual ideas. And I think it's great. And I'm just kind of partly joking about the fact that it's thankless because people only notice your mistakes. But I mean, implicitly, they notice your successes because they're using it every day to actually get their work done, and they're thinking in terms of the things you figured out. But they don't notice what happened there. It just seems obvious to them, which is the way it should be. But so, you know, a part of the reason that I didn't explore physics more, well, the main reason was target market didn't seem to want it. I had a lot of other things I thought were really interesting. And I kind of put it on the side, and I kind of thought, you know, someday I want to do this. And I kept on thinking, you know, I kept on trying to figure out, is there a way to do this project that will lead to people, you know, will be sort of a happy story. And that's part of, that's part of what's happened here, is I thought, you know, how can I do this project if the target market for this project is people who've been doing hardcore physics in a different direction? And I didn't know that the project would end up dovetailing so nicely with what's been done in other areas of physics. That's not what I thought was going to happen. So my assumption was we would build a new sort of prong for how physics would work, and it would be sort of incompatible with the existing prongs. That's not what's really happened. What's really happened is actually something much nicer, much sort of happier ending here. But so that's what I thought was going to happen. And I thought, gosh, you know, then I'm going to be in the situation where the target market doesn't want it. It's like, please don't do this project type thing. And then how do I do this project so it's a happy project? And so I thought, eventually I realized as kind of the connectivity of the world started to increase, more social media, live streaming, all this kind of thing. It's kind of like, we can do this project in a way that there's a very important spin-off. Even if we don't even succeed at the project, the spin-off is education, and the fact that there are people who are interested in physics and who maybe can get more interested in physics because they get to see up close what's involved in trying to, you know, ascend the Mount Everest of physics, so to speak. And so what I kind of realized is the way to do this project is as a public project, because worst case, we don't succeed in getting to the summit. Worst case, and I've gotten a lot more confident now that I've seen what we've actually been able to do. But worst case is we don't succeed, but nevertheless, the climb should be very interesting. And people who are interested in science, in understanding what's involved in science, people who are students who are thinking about, should I commit to studying a lot of physics, mathematics, whatever, to see things being achieved there, and to see the sort of excitement of the adventure of trying to find the fundamental theory of physics, I thought that was worthwhile. And that's what, and that's kind of one of the motivating factors which caused me to sort of think about in recent years. That's how I would do the project. As I say, I thought the project was going to be a lot harder than it's ended up being. I mean, there's still plenty of hard stuff to do, but we got a lot further. We made it, much further than the base camp. I thought we were only going to make it to the base camp. We've actually, I don't know my Everestology well enough, but we made it up to a definitely higher place in getting to the summit, so to speak. And I have to say it's been really nice for me to see just over this last week, as we've been doing live streaming of the things that we've been working on. Seems like people are finding it interesting, and that's great. And that's and I hope some of the people who have been paying attention to this, that they find it at least somewhat inspiring for whatever it is, whether they want to work on these kinds of things specifically, or whether they want to work on other kinds of things about physics or science or technology. I hope that seeing this process of trying to get to the top of this Mount Everest of science, so to speak, I hope that that's something that people find interesting to see. I mean, I think we are in a sense merely the kind of the sort of the climbers who are trying to do the climb, and there's probably as much to see that's interesting in terms of watching the climb happen as to be the one putting in the hard work of actually trying to make it up the next piece of the mountain, so to speak. Okay, so next question here. There's a whole lot of questions here, lots of interesting things. All right, let me try and go down some of these. What happens if someone finds the rule? Well, that'd be great. I don't know how easy it's going to be when we say, here's a rule, let's look at its consequences. I don't know how easy that's going to be. I'm a little bit, I've been more pessimistic than is justified about this project. That is, I might say, well, you can find the rule, but you'll only be able to find what it does for 10 to the minus 100 seconds. I think things will be going so well that probably that's not going to happen. Probably it's going to be the case that once you've found this rule that has all these various attributes, you'll be able to see, gosh, it's going to imply this, it's going to imply that. And then there'll be some hard work to do. It'll be like, okay, this rule implies there is a particle with a mass of 10 to the minus 5 electron volts, and it has these properties. Or this rule implies that the initial density spectrum, perturbation spectrum of densities in the early universe is this or that. This rule implies that if you try and make a quantum computer with this that runs at this speed, you'll see this thing happen, those kinds of things. I think what will happen is, it will be, I don't know whether it will be a slam dunk, okay, here's the rule, now everything just crumbles, and we start to see everything just fit together. Oh, okay, we got this gauge group, we've got this dimensionality of space, etc. I don't know if it's going to crumble easily, or whether it's going to be a hard job. I think it is likely that some of the predictions from the rule will be non-trivial to make, that it'll be the same kind of work that had to go into quantum field theory or general relativity to figure out their predictions. I mean, knowing that gravitational waves will be produced in this way by the merger of two black holes, that's not easy to figure out. That's a big, complicated computation to figure out what you should expect to see. Will the gravitational waves be intense enough that we can detect them, et cetera, et cetera, et cetera. So, I would expect the same thing here, that in getting to we can actually turn a telescope to this and go see whether it's true. That may have a lot of sort of technical work to be done to actually get it to the point where we can say, okay, you turn the telescope, you look at this, black hole at the center of the galaxy, you look at, you measure this particular 2-photon correlation function, and you will see this, and it should be, you should get this correlation and not that correlation. I don't know how easy. I think that's going to be a lot of sort of very, in a sense, traditional hard work of clever physics to figure out all of those details. Okay. Okay, so yeah, so I see why I can't parse these handles, but I blank is asking about being able to go back to some of these live streams and find the aha moments. Yeah, I've been curious to do that actually, because we recorded all the sort of working sessions that we were doing, and we're just sort of prepping them to put them online. And I think that there will be. I'm a little bit. I'm sure there'll be a lot of stuff there. I mean, I remember conversations, particularly between myself and Jonathan, where it's like, I think there's one certainly about the path integral, where it's like it went on for hours and hours and hours of, how does this work? How does this work? No, that can't possibly be right. What about this? What about that? What about that? And I think that was one of these ones where it's getting really late. And I'm like, let's take one more run at this. Let's see whether we can get it. And we got it. And so there are probably some fun things like that. And there's probably a lot of, some of these things, once we've seen how they work, it's like, wow, that's pretty obvious. In fact, yesterday, we were working on quantum spin and angular momentum. And I am certain that that's going to be one of these ones where we're just going to get it. And I had a new idea last night about how we might get it. But I'm sure, I'm expecting, I will be disappointed if we don't, soon we'll just see how that works. And by the way, if somebody else can see how it works before we do, that's fantastic. But that's going to be, I think, one of these, and it's kind of some of these things, once you get it, it's pretty obvious you got it. It's pretty, things just fit together. And, I've said many times in this project, it's not supposed to be this easy. This is what happens when you have sort of a new paradigm for thinking about things, is there's low-hanging fruit. And it's really fun to pick that stuff. Okay, a question here. If we advance this project, do you think there'll be a moment where the knowledge that's obtained is powerful to the point where it impacts one's daily, one's life drastically? Here's what I think about that. If you look at general relativity, it's 100 years old, there's still almost no everyday effect from general relativity. Quantum field theory, again, almost no everyday effect. I mean, my favorite sort of elementary particles that I studied a lot in my youth, even the strange quark or the charm quark, they're really cool, but there's absolutely nothing in technology that involves strange particles. There's absolutely nothing that in technology that involves neutrinos. There's absolutely nothing, we can, neutrinos implicitly are used in nuclear reactors and so on, but they don't have an active role. People thought you might be able to do tomography of the Earth with neutrinos, but that hasn't panned out. In any case, the things from 100 years ago in fundamental physics still haven't had sort of a daily life impact. I actually think if we look at the history of science and the history of fundamental theories of physics, the thing that probably had if we look back at, I think there will be some impact, but it will be more at a conceptual level than at an everyday device level, so to speak, probably. I'll say a little bit more about that in a moment. I think the place that, if we look at the history of fundamental physics, one of the things that was sort of a major moment in physics was the whole Copernicus story. It had been the case from Aristotle, from the ancients, et cetera, et cetera, et cetera. The Earth is the center of the universe. Obviously, the Earth is standing still. We can all tell that. The sun must be going around the Earth, et cetera, et cetera, et cetera. Ptolemy had really pretty good theory for how that worked. Pretty accurate predictions of things based on that. Then, Copernicus did this fairly technical piece of work showing that actually the theory was a bit simpler if the Earth went around the sun. And, I don't know how much effect the technical work had. I'm fond of pointing out that when we did our sort of precision eclipse computation using a bunch of things other people have built, what we were fundamentally doing was using 10,000 epicycles to predict where the position of the moon would be. I mean, the way that those were derived uses things that aren't epicycles, but in the end, you're turning everything into epicycles, into sort of Fourier or Poisson series or whatever. Actually, much like the Babylonians apparently did. But although they had zigzag functions apparently that weren't continuous. But in any case, what effect did the whole Copernican, theory have? Well, it had a big effect on the way we think about the world and the fact that, it's like science has things to say that aren't obvious to us. I think before that time, most of what science had said, you could kind of reason your way through. It wasn't a thing where you had to say, just trust the equations. They tell you that the Earth can go around the sun. And that was an important moment for what has become modern science. And so, there are things that I think come out of and then the sort of paradigm of modern science that started to develop in the 1600s of mathematical equations. That's, put your trust in mathematical equations, so to speak. And that has led to a certain kind of paradigm for how one thinks about science, and a certain kind of, there is a force, things exert force, there's momentum of things happening. Those are all terms from mechanics that date from, the 1600s, and they are things that we now kind of suffuse our kind of everyday thinking about things. I think increasingly we will come to think about things computationally, and ideas like computational irreducibility, which kind of is a core thing to understand in this model of physics, that's something that will be an increasing thing that we need to really think about in our everyday lives. I mean, last summer, I happened to do some testimony for the US Senate about kind of AI content selection for web services and so on. And it's kind of like, what should you be showing in a newsfeed, and how does that work? And how can you know that the AI isn't going to do the wrong thing? Well, you might say, well, just look at what the code for the AI says, and realize, well, that just won't work because of this phenomenon of computational irreducibility. And in a sense, computational irreducibility is, after the sort of long run of how successful science can be at telling us things, computational irreducibility is kind of a little bit of a, whoa, from inside science, there's something that is kind of telling us something about the limitations of science. And it's really, it's a kind of the long tail of Gödel's theorem and so on that eventually has led us to things like computational irreducibility. And I think that the sort of philosophical implications of understanding that the world is a computational place will be perhaps, to the everyday person, more immediately significant than the technical kinds of things. Now, are we going to get technology from this theory? Interesting question. Don't know the answer. Some of the length scales and time scales and so on are really pretty far away from anything we humans do. I mean, during the period when I was in the early 2000s, when I was sort of thinking about doing this project and starting off doing this project, one of the people who was a research assistant of mine, people would ask him what he was working on, and he would say, "I'm trying to invent warp drive." And that usually stopped, I think, any conversation anybody had with him about what he was working on, because they just thought that was totally nuts. But in a sense, the question in a theory like this, can we construct, given the raw materials that we now potentially have from this theory, can we figure out, is it possible to make, a faster than light thing? Well, maybe we can prove that's not possible. Or maybe we can say, well, there's this weird configuration of things, and somehow you can build up to make it possible. I don't know for sure. I don't know whether the things that are the immediate sort of things you could do with this theory are things that involve you to have a pet black hole or something to be able to work on it. I mean, back when LIGO discovered gravitational waves, I wrote a blog post about black hole technology, because I was curious. It's also about how one figures out about how black holes work. But I was curious, let's jump ahead. Now that we know black holes are real, let's jump ahead to a time when we can have a pet black hole, so to speak. And let's ask the question, how could we build technology out of black holes? Or alternatively, if we were sort of the conceptual extraterrestrials who are operating on huge scales and can move black holes around, what could we do in the universe? I think actually what we've discovered in this project, this maximum entanglement speed, actually puts some limitations on what this sort of galactic size intelligence and so on is capable of doing. But that's a different story. Okay, so there's questions here about practical innovations, new energy sources, propulsion methods. So I think I've been trying to address that. I think it's pretty far away from, but having said that, I'm looking forward to being proved wrong about that. I think, relativity, for example, even relativity, it's challenging to find examples in everyday life that are examples of applications of even special relativity to things. Now, certainly implicitly, it's very much the fabric of a bunch of theories and so on. But if you say, like for example, one of the things, okay, I'll give you an example. At the Stanford Linear Accelerator, which is a mile or two long particle accelerator that accelerates electrons through a bunch of electric fields and so on. There are these drift tubes, which are the things that in which the electrons are sitting when the electric field is sort of going in the wrong direction. So electron goes, it's accelerated by the field, and it enters this kind of copper cavity where it's shielded from the field, comes out the other end. By the time it comes out the other end, the field has reversed sign and is again pushing the electron. Okay, so the drift tubes, if you look at them, which you can't because they're in a vacuum and you don't get to see them anytime, but if you look at pictures of them, you'll see that the drift tubes, initially, the drift tubes are getting longer and longer and longer because the electron is going faster and faster, and so it will take you have to have a longer drift tube to deal with the fact that the fixed frequency of the field that's pushing it, it will have to be sort of hidden from longer from that field. Eventually, the drift tubes start to be the same length, and that's a sign of the fact that the electron that's a sign of relativistic time dilation and mass increase and so on, that those drift tubes are starting to be the same. Like, that's an incredibly obscure, the fact that I had to go to that extreme to give you an example of where you can sort of see relativity in action is kind of disappointing. I think one of my favorite non-examples is the GPS satellites, where they are going, they're in orbit, and they need very precise timings in order to give the sort of distance measurements. And the question is, do they, as they go around their orbits, does it matter that they have relativistic time dilation and that they're in larger and smaller gravitational fields and so on? Well, actually, the clocks of the GPS satellites are back corrected, because it's easier to back correct there than it is to have sort of relativity running in your, in your car GPS or something like this. So it's kind of an example of where you might have had relativity, and you kind of did have relativity, but it's only in the eye of the computer inside the GPS satellite. I don't know, maybe other people know other examples, but I think that's after 115 years of special relativity, I think we're still not quite in, well, okay, one big example obviously is the E=mc² story, and the story of nuclear fission and so on. That's for sure a big example. And that's an example which didn't come out of the sort of the space-time aspects of relativity so much as the other implications of relativity. And could we get something like that here? Maybe. Be interesting to see. Hopefully, just don't know. Okay, there's a question from IC. How does this compare with doing science alone in a room and remembering the time that I spent working on the NKS book? This is a lot more fun. Working on the NKS book for 10 years as sort of a pure hermit it's a grueling thing to do. My gosh, I wouldn't wish that on anybody. It is the strongest exercise in tenacity that I've ever had in my life. I mean, I wasn't a complete hermit. I was running a company. If you compute it, you'll realize my 3 oldest children were born during that period of time. So I wasn't like utter hermit, but I was pretty much as I'm doing now. I wasn't going out of my house for weeks at a time, so to speak. And I was working, and I think I didn't probably work on that project as efficiently as I could have done. I think that the level of kind of perfectionism that I tried to exercise there, while very satisfying to me in retrospect, was very grueling and made the project take a lot longer than it would otherwise have taken. I think also, I had a number of talented research assistants and so on that project, but I think I probably could have had a stronger sort of, I could have invested more in sort of help for the project. I think it's, in my life, there's no way I could do a project that requires that level of grueling tenacity for that long ever again. It's not like I shy away from big, daunting projects, but the level of 10 years as a hermit working on a project, I think that's you don't get to do very many of those in a lifetime, and I think I've done my one of those. And I think that arguably, I would have had you write a book that's 1,280 pages long, and you say, well, what were the most important pages in that book? Well, it's probably about 500 or 600 of them. And, other ones probably less important. And I probably could go and look on the web and find out, how often people and myself have looked at different pages of the book. But you can't know until after you've done it which ones are going to be the important pages. I think probably in an optimal world, I would have kind of not even talked about fundamental physics in NKS because it sort of seemed to distract some people from the main point of introducing this kind of science. But I'm not sure that kind of science, what I really wanted to do was to give enough use cases that people could understand roughly how you apply this kind of science to different sorts of things. So that's kind of why I did that. Let's see. Do we get paid by Twitch for these streams? No. What do I get out of it? I kind of like sharing stuff. It's kind of fun. And also, what I'm really hoping, and it started to happen, is that we get useful feedback that's helping us to do our project better. Plus, realistically, I like trying to explain things to people because part of what I'm doing is explaining them to myself. As the kind of discipline of, for example, I've been doing a bunch of live streams, particularly during this pandemic time, for kids, doing, for example, science Q&As for kids, and I did a briefing for kids about the physics project. And that's really interesting to me because there are a bunch of things I figured out as I was doing that, both as I was thinking about what I was going to do for it and as I was actually doing it, where I realized, oh, that's an interesting way to understand that. And it's these steps of understanding that really take me to the place where I want to go, which is really having a deeper, broader understanding of, in this particular case, these questions about physics. So that's really nice for me. And frankly, I just I like the idea of sharing these things. I'm very excited about the ideas we're talking about, and it gives me a satisfaction to be able to share those ideas and hopefully to give other people some fun thinking about them too. What are the plans for archiving videos from these live streams? Yeah, we're archiving all of them. I guess probably maybe this week, maybe next week, we'll start putting up all of the archives from the creation of the project. I think these particular live streams we're already up on the website as archives. When we're doing live streams that have real sort of hands-on notebook type content, we're using the new video capabilities of Wolfram language. It just came out in version 12.1 to be able to make kind of thumbnails of what happened during that live stream so that they're easier to search. We also have run these live streams through speech to text that we have in Wolfram language. And we've got these kind of, they're not great as transcripts, but they are pretty interesting as word clouds. And I hope will give an idea for sort of what happened in these live streams and which ones are worth particularly looking at. And particularly these live streams that are mostly me yakking away, talking. I think these are getting carved up into podcasts for people. I think we've done that for, well, I'm not sure if we've done it yet, but I think I did one of these right before the launch of the physics project about history of physics that might have turned into a podcast already. Let's see. Okay, so there's a question here from Pirik Buddha. Software engineer, he or she says, a software engineer doing their master's, want to do my thesis on simulation of something from physics. Gosh, I don't know, hard to know without asking more questions. There's a lot of interesting things. If you're interested in fundamental physics, well, I kind of recommend this big project we're doing about fundamental physics. In terms of other things in physics, there are just so many questions there's so many kinds of systems in sort of everyday world systems where actually there isn't a good model for them. And, whether it's, I don't know, granular materials, soft materials, whether it's some things about, I don't know, I'm looking outside, leaves blowing around, what's the actual, I don't know, I'm sort of making it up of things. There are a lot of everyday physics questions where we haven't traditionally had great ways to make models because the models that have been made have tended to be based on, we always think we have to work from the differential equations up, and it's a pretty long way to get to, the sand, so to speak, literally from differential equations. But there are models that can capture the essential features of those systems much more easily. Now, those models are happening at the level of things like cellular automata. They're very different from the kind of models that we're trying to do with our truly fundamental physics here. I would say that, well, okay, having said that, okay, I would make a suggestion that if you want to be really modern, take these kinds of network-based models that we're using for fundamental physics and try and understand some other kinds of processes, maybe ones that occur in physics. In terms of these models, I think there's probably some interesting things to do there. And my meta suggestion would be apply to our summer school, because that is what that's all about, is figuring out projects that are a good match for people and will lead to interesting results. And it's many years ago, I used to be a professor, like in an actual university, so to speak. I've mostly been a tech CEO for the last 32 years now. But is that the right period of time? Yeah, it sounds, no, maybe more longer than that. 33, 34 years. But anyway, my one sort of moment of extreme professoring during the year is being involved with our summer school. And one of my responsibilities there is, we have, let's say, it's usually about 75 people who come, and it's like, okay, there are these people, they have these interests, these skills, there are these projects that I've sort of thought of that are worth doing. Let's try and match them up, or let's come up with new projects. And that's kind of one of the things that I end up doing, and I find a lot of fun, and a lot of great projects have come out of that, some of which have turned into whole careers for people, which is really, really cool to see. How long are you going to keep the working materials for this out in the open? Well, I hope we're just going to keep doing that. I mean, unless something terrible happens, that's the plan. This is uncharted territory. Nobody's ever done a science project like this. I think that we are trying to both invent new science and invent a new way of doing science. So far so good. We're just at the we're just out of the starting gate, so to speak, in terms of what's going to happen. Terrible things could happen, but so far I'm really pleased with what's been happening, and I expect to continue this way. So there's a question here about, suppose we find the underlying rule for the universe, how do you imagine or foresee this rule could be practically applied to further scientific discoveries and technological innovations? There's going to be tons of science at the physics level to do. There's just tons of stuff. I mean, if we can figure this out, there's going to be, every piece of understanding particle physics, gravitation theory, early universe, quantum computers, plus probably a bunch of completely unexpected phenomena and completely unexpected kinds of things. For example, it could be that there's a lot of stuff that happens in the universe that's more kind of in the dark matter regime, where there's a whole vast physics of what's going on there that is right now hidden to us, and where we don't have good experiments to probe it, but we might have a theory that can really tell us things about it, and where we can start working that out and seeing little places where it sticks its neck out, sticks its head out of the water, so to speak, and we can actually tell what's going on at the level of the things that we can do astrophysics on, and so on. I think that, as I've mentioned before, the sort of core models that we have here are going to be super interesting for things like distributed computing, possibly theory of evolution, probably a bunch of other possibly things about mesh networks, a bunch of technological kinds of things. I mean, unwittingly, we've ended up sort of backing into a different way of thinking about what one might think of as ambiguity in bulk. Because what's happening is that in these models, you're having all these different ways, all these different asynchronous, in a sense, asynchronous, because that word doesn't really mean anything until you have a notion of time, but all these different events that are happening, and all this sort of ambiguity about what event happened. And that's something that's come up in thinking about distributed computing, deadlocks and race conditions, all these kinds of things. But it hasn't really been thought about in bulk. What happens if the whole, if you've got gazillions of these things happening? How do you make a kind of conceptual framework for thinking about that stuff? And in a sense, ideas from things like general relativity or even relativity about reference frames, things of this kind, ideas from quantum measurement theory, ideas from sort of quantum computing, give us, I think, a way to think about ambiguity in bulk. And I think that is very interesting as a way of thinking about things like distributed computing. And I think that will have probably the most immediate, I'm going to guess that's going to be the most immediate technological consequence of this, of the work that we're doing on fundamental physics, is essentially spin-offs for using physics-like ideas to apply to distributed computing. And I think there will be some other things. As I say, I mentioned theory of evolution. It's like, what is the overall meta theory, both of evolution in the large, in the history of life on Earth, and evolution in the small, whether it's in bacteria with antibiotic resistance, or whether it's in oncology and cancers and so on. the microevolution of cells, and how does one think about that, and what's the sort of mathematical framework or the mathematics-like framework for thinking about that. It's been a question, and I'm just to throw out one thing along those lines. People do simulations of natural selection. Okay, I've done them myself. Here's one of the things. How much survives? That is, you have all your little critters, and they've reached a certain stage, and you say, only the winningest survives, you might say. We say only the winningest and its 5 runners-up might survive. But it gets very hokey. And there isn't a very precise way to do this. There's not a very precise way to think about, the same thing happens in genetic algorithms. How many of the sub-leading contenders do you have survive? I think that's one of the sort of imperfections in having a model, and I suspect we may have a way to resolve that. Completely unexpected. I mean, it's purely a matter of the technical infrastructure that's being built from this very minimal model. Has nothing to do with physics as such, except that some of the terminology from physics might end up, it might be that, speciation is like the formation of event horizons and so on, of things you can't easily cross and such like. But so that's I think the way that will see application first. And there are probably some. I mean, I wouldn't be surprised if there are some applications to chemistry from thinking about these graph rewriting rules, because essentially chemical synthesis is in some ways an exercise in graph rewriting, and one can think about. In fact, this is not a bad idea. In fact, when one thinks about chemical synthesis, one is basically trying to figure out, given this starting chemical, given this ending chemical, given the set of moves that you can make on the graph that represents the chemical, can you get from beginning to end? And usually there's this kind of tree of possibilities. And as you think about these reactions and their rates and so on, you're kind of thinking a little bit about something that's like the multi-way system. You're kind of being asked, a little bit like the way you prove theorems in mathematics, you'd be asked, can you find a path? Can you find a proof that gets you from the beginning to the end, so to speak? Can you find the synthesis pathway in chemistry? And actually that leads me to another question, which I had not thought about. Sorry to be doing this in real time. But one of the multi-way systems, I first started thinking about multi-way systems in the early 1990s, partly as an idealization of mathematics. So all of these different, when you are doing mathematics, sort of an idealization is, can you prove a theorem that says that A equals B? And all you know is that X is equal to Y and Z is equal to W. Those are certain axioms. And can you thread those axioms so that you go from A to this, to that, to the other, just using those axioms, and then get to the answer B? And that's some automated theorem proving, and the kind of thing we can do in Wolfram language now. And actually a bunch of that stuff Jonathan worked on in our practical technology. Can we, given a set of axioms, can we prove this theorem by finding this path from beginning to end? And that's like kind of saying, in the multi-way system represents the set of all possible paths, the set of all possible proofs. Can we find a particular proof that gets us to a particular place in the multi-way system? So the question here is, can we invent a theory of metamathematics that is a kind of an aggregate theory of metamathematics? So you can think about mathematics as, we've got these axioms, we're going to find proofs based on these axioms. Certain proofs have been found in the history of mathematics. There are about 3 million theorems that exist in the literature of mathematics. Those represent certain paths in this multi-way system of all possible mathematics. And in a sense, what we're doing is, as we build mathematics, we're finding these paths that sort of fit together in a certain way. And so one question that you might ask is, what's a kind of meta theory for the progress of mathematics? I mean, one has the impression that what happens is we reach certain sort of plateaus of abstraction that allow us to go further in the construction of mathematics. And so there, I haven't figured it out. I'm just thinking about this in real time here. Thinking about kind of the bulk theory of metamathematics in terms of some of these bulk features of the multi-way system and multi-way causal graphs and all these kinds of things, maybe that's applicable. I think I mentioned another live stream that I wouldn't be surprised if some of this thinking about multi-way systems and is applicable to thinking about machine learning and particularly training of neural nets and so on. See, what tends to happen is when you train a neural net, you're thinking about, well, I'm going to make a bunch of random choices. They're like one path in the multi-way system. If somebody says to you, just consider the ensemble of all possible neural net trainings, probably somebody's going to say, that's crazy. That's just too big. What could you ever conclude from looking at the ensemble of all these possibilities? It's hard enough to just train one neural net, let alone to train the space of all possible neural nets. But one of the things that's come out of this physics project is this thinking about how to deal in bulk with all of these branching possibilities, and kind of the way that, in fact, we learnt from the history of physics, from the history of quantum mechanics, the history of general relativity, we've kind of learnt from the big ideas from physics, we're learning things about how to think about that general problem, and that general problem occurs in lots of other places. And so this may give us kind of a new piece of leverage to make progress in those other places. Okay. Let's see, there's a question here from Rosalind Franklin. I wonder whether we're too late for the original X-ray crystallography one, so I don't know whether that's a homage name or a coincidence of names. But person says, I have a chemistry background with what areas could I work with? Well, depends on what kind of chemistry. Things to do with graphs. I was just mentioning some things about chemical synthesis, actually. I think there are probably some interesting things to do to use the models that we have as ways to think about sort of a meta theory of chemical synthesis. I think that would be an interesting way in terms of the physics project as such. There might very well be things to do with graphs and with studying kind of the empirical study of kind of what happens with different kinds of graphs and their evolution that will be worth doing. I think I'm going to say again, come to our summer school, apply to our summer school, because that's the way to kind of, that's our best chance to match up kind of background with project, so to speak. Okay, question from Leo here. In the backstory blog post, I mentioned that I had an idea that solved a nagging problem that I had with my approach. Here's what happened. So back in the 1990s, I was like, what could be underneath space and time? What sort of doesn't have the structure of space and time yet, but sort of might have space and time emerge? And what I thought about then was networks, where you have just a bag of points and they're all connected in some way with a network. And that's pretty much what we're talking about now too. But back in those days, the most minimal network that I thought about was a trivalent graph, just a graph where every point, every node in the graph is connected to three others. And it's pretty easy to see that a trivalent graph is capable of emulating any other kind of graph, a graph that has 5 connections to a node and all those kinds of things. But so I had that idea, and I then started looking at, well, what possible rules are there for rewriting trivalent graphs, for saying, if you have a piece of graph that looks like this, it will be transformed into something that looks like that. So I did that. I came up with lots of these rules. But what was very awkward was that most rules I could just write down would not be valid rules for trivalent graphs, because they would say things like, well, again, as is so often the case in the progress of science, I was confused, because in the end, the things that held me up are things that we now understand and shouldn't have held me up at all. But for example, here's an example of something held me up. I was thinking, you have a graph and has a certain degree of symmetry. And a lot of the rewrites that you would write down, the graph that it turns into has a lower degree of symmetry. And so then how do you decide which of the possible, essentially, orientations of the graph come out from that rewrite? I was thinking, gosh, you can't do that. You have to have only rewrites where you have a higher degree of symmetry in the output than you had in the input, because then there isn't any ambiguity. Of course, what we've realized now is ambiguity is your friend. And the fact that there's sort of ambiguity in the way that things can come out, that's okay. That's just another branch of the multi-way system. But I didn't understand that. Even though I knew about multi-way systems, I didn't understand that point back in the mid-90s. And so the way I had thought was well, we've got these trivalent graphs, but it's a very fragile thing to find one that is a valid rule to try doing things with. You know, in cellular automata, for example, any rule of a certain class is a valid cellular automaton. It may not do anything interesting, it may just die out, whatever, but it's a valid rule. There's nothing to get to the starting gate of let's explore this rule. There's no impediment to getting to the starting gate. But without my trivalent networks, I thought there were serious impediments in kind of getting to the starting gate. What I then realized with these kind of symbolic transformation rules that turn into these elements and relations, turn into these hypergraph rules, there are no such things. Any rule like that you write down is a valid rule and you can go investigate it. It may not do anything interesting, but you don't get stuck saying that's not a possible rule, so to speak. Now, as it turns out, embarrassingly enough, when I look back, having understood that now, there wasn't really a problem with these trivalent graphs. But I thought there was a problem, and that's one of the things that had made me very frustrated. It's like, it's too arbitrary. You know, why are we dealing with trivalent graphs? Is that really, you know, is the number 3 really critical somehow? Well, I don't think so. And so what I really like about this elements and relations mechanism that we have in the current model is it's just so minimal. It's just, there's just nothing there. And I also realized, again, somewhat embarrassingly after the fact, that the core idea of transformations for symbolic expressions, that is the core idea of Wolfram language, that is the core idea of the system called SMP that I built back in 1979, it is the same core idea. And it took me, you know, whatever, 40-something years to kind of translate that idea into something that could now be used for fundamental physics. It's sort of embarrassing how long it took, but it was sitting right in front of my nose. Which is kind of embarrassing, but you know, that's the nature of science. That sometimes you know, there's you have to have a certain amount of ambient knowledge and a certain amount of ambient set of things that are going on, and then in my experience, you finally sort of understand what the point is. You finally understand how to ask the right question, and then you can really get somewhere. And for me, at least, you know, the fact that I've worked on a lot of different areas, and I've been kind of exposed to a lot of different fields by the fact that we've been sort of putting them into Wolfram language and trying to sort of build out our full-scale computational language to include all these different kinds of knowledge. That's been super helpful to me because it means that I have a good, you know, when I know what the point is, I have a pretty good lexicon of things to draw from in terms of how to sort of realize that point that I then realize. But the process of understanding what the point is, that is a painfully slow, multi-decade process. And, you know, I have to say, this physics project, I'm so excited that this project has worked out as well as it has. And I really didn't expect that. And it kind of has led me to sort of inspired me. I have at least one other big project that I really want to do this project has sort of inspired me to say, I've actually got to do this project. And well, there's a couple of big ones, but the one that I'm going to do is one, I call it symbolic discourse language, sort of a way of representing everything that we talk about in the world in sort of a symbolic, precise, computational way. But that's a different topic. Okay. There's a question here about the simulation argument, which I think I've answered too many times here, and I should get better at answering this. Well, okay, wait a minute. Actually, is from Crumpeteer asking, what do you think of people today thinking that the universe operates like a computer simulation, just like how people used to think the universe operated like clockwork before that? Okay, that's interesting. I mean, so in a sense, we are the victims of our sort of ambient intellectual stage of our civilization. So back in, you know, ancient Greek times, when people are thinking, how does the universe work? Okay, they figured out the universe might consist of lots of identical things all put together. Pretty good idea. That's basically the idea of, you know, the elements and atoms and things like this. Even more so, it's the idea of what happens in our new fundamental theory of physics. But, you know, if you were Democritus back in whatever it was, 5th century BC or something, you know, you didn't have the lexicon to talk about things in terms of, you know, programs and computational rules and things like that. And so to talk about things in terms of, I don't know, lots of identical platonic solids, pretty decent idea. You know, Lucretius, when he was talking about, you know, the world could be constructed in the way that sentences are constructed from words using a grammar. Pretty good idea for its time. I mean, I think this, the concept of the soul, for example, which one sees in a lot of coming out of a lot of lines of thought, is kind of a grappling with the idea of computation. What is there about thoughts? What is there about brains that isn't just the wetware, so to speak? What is it about thoughts that is something that goes beyond the wetware, so to speak? And that's, in a sense, today we might explain that as, oh, it's this abstract thing we call computation, or it's this abstract representation of data and memories and things like this. But the notion of the soul was a pretty decent approximation to that based on the kind of thinking that existed at the time. Now, similarly, when clockwork was a thing, then people were talking about the universe works like clockwork, because that was kind of the way of talking about things at the time. Now, today, when I talk about things about, programs halting and things like this, people have some understanding of that because we have this ambient experience of computers. Now, could we have invented these kinds of things about thinking about the world in terms of simple rules without computers? I think so. Somebody just recently showed me a Babylonian tablet in which some Babylonian had worked out 8 different choices for possible rules for making mazes. And I'm really hoping one day somebody finds a Rule 30 on a Babylonian tablet, and that actually, all these things that we've done in modern times are really 4,000 years old. But this was the closest I've seen to people exploring kind of different possible underlying rules. That was from 4,000 years ago. Now, could the kind of things that we're thinking about today have been thought about at that time? It's the same thing about, well, yes, but there's a whole sort of ambient platform for thinking about things that doesn't exist at the time. I mean, we know from the Antikythera device that there were clockwork computers in antiquity. We don't know how widespread they were. And, I certainly wonder, in sort of the alternative history theme, if those things have been really widespread and they'd really survived after the Roman period and so on, and they've been well known. I mean, they were reinvented in the 1600s, but if they'd been well known throughout that period of time, would the development of science have been different? And would one see much more of a computational way of thinking about things? I think the answer is probably yes. But so computation and being able to talk about computers helps in both in developing the sort of ambient understanding of what's going on, and so for example, in Gödel's time, one of the things that Gödel achieved was essentially to build a compiler for arithmetic that will take sort of mathematical statements and compile them down to arithmetic. But he didn't think about it that way. Now, the fact that I can explain to you what Gödel did was to make a compiler for arithmetic, that's progress, because I'm leveraging the fact that many people will know what a compiler for a computer is, that takes a computer language and compiles it down to machine code. That's something we now understand in a very general sort of societal way. But of course, Gödel didn't know that. And so his description was quite obscure, probably even to him, certainly obscure to other people, what he was really doing. Turing made it a bit clearer. The fact that we can even discuss those kinds of things is the fact that we have sort of this ambient societal understanding of computation is important for being able to communicate and having a platform for thinking about things. One of the things that I think is an irony of history is that the very idea of abstract computation is so recent. Because one of the things, when you talk about mathematics and you say, this is what the ancient Greeks did, this is what was done in the 1400s, et cetera, et cetera, et cetera, to some extent, the education that people are given in mathematics, to some extent, recapitulates the history of mathematics. Not entirely, but to some extent recapitulates the history of mathematics. There's a tendency, particularly in physics education, to recapitulate the history of physics in its education, to go from classical physics to quantum physics, et cetera. But, there's a question of what is that the inexorable path to, for example, modern mathematics or modern physics, or does it not need to be that way? And I think one of the great examples of it not needing to be that way is the idea of programmable computers, because youngish kids, at least based on my samples, they get that idea. They don't need to know mathematical logic. They don't have to have studied lambda calculus to get the idea of what it means to program a computer, to have a machine that is programmable. Yet in the actual history of human thought, that was a late stage idea. And that idea only emerged after people had thought about lambda calculus and Gödel's theorem and who knows what else. So it's sort of an interesting example of something where the history didn't need to happen, I think, in the order that it happened. In other words, I also think, for example, Leibniz back in the 1600s, I think was pretty close to the idea of a universal computer. I visited his archive a few years ago, and I was really curious to kind of look through all his papers and see whether I could find a picture of a Turing machine, so to speak, in his papers, because it wasn't even clear to me anybody had gone through them to the point of being able to notice that. I didn't find a picture of a Turing machine in his papers. And I think most of the things I could see were things where with a modern eye, I could understand what he was doing. They were not things where I say, I don't know what that is. Maybe that's a Leibniz version of a universal computer. But I think Leibniz conceptually was quite close to the universal computer idea. Whether in what terms he would have explained it in the 1600s, I don't know. But it's sort of an interesting sort of ahistorical. It's something where the progression of history, I think, was not predetermined there. Let's see. Okay, so there's a question from Camille about if we see from models that we can model the whole universe in terms of zeros and ones, will that mean that, why do theoretical physicists hesitate to admit that the universe could be computational? Well, because there's a long tradition that dates back to Galileo and Newton of great success in using essentially the methods of calculus to study the physical world. And it's been a long ride, and it's been a good ride, but I don't think it's a ride that's going to take us to the end. I think that it is inevitable when fields develop and they're old, sophisticated fields. They have a methodology, and the methodology revolves around using calculus. I mean, in a sense, some part of physics, as physics is done, is it's the application of calculus to try and figure things out about the world. That's a little bit of an unfair characterization of physics. And to be fair, physicists often do things more general than the things that would be considered, physics for physics' sake. But I think there has been a lot of resistance. I know when I started working on this in the 1980s, there was sort of an assumption, well, there's computers and they do things digitally, and then there's physics and it does things in an analog way where it can precisely work out this precise real number. The position of this object is 0.7258464, blah, 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 an infinite number of digits. Now, one of the things that's been interesting in theory of computation is nobody's really ever managed to make a robust theory of real number computation. In integer computation, as done by Turing machines, lambda calculus, register machines, cellular automata, these models of physics that we have and so on, all these models, even though they're very different in their underlying structure, end up being able to do the exact same set of computations. And that's the kind of the Church-Turing thesis. That's the raw material for my principle of computational equivalence. That's a really, really remarkable fact that we've learned over the last 100 years, that all these different things that we might think of as being different ways to get computation done, they're all ultimately equivalent in the set of computations that they can do. The same thing doesn't happen for real number computation. There's no similarly robust, somebody has one theory for how it might work, another person has another theory for how it might work. There hasn't emerged a sort of robust idea for how it might work. And maybe that's coincidence, maybe it's not coincidence. I think that, so even at that level, there isn't a theoretical framework to talk about these things. And then, more seriously, there's the question of, okay, let's say we were going to try and figure out, we're trying to try and leverage, let's say physics really does deal with infinite numbers of digits. How do we use that? How do we prepare an initial condition for a system that is so precise that we're using 100 billion digits in that initial condition so that we're able to do a computation? Well, we just can't do that. We don't have a way to prepare the universe accurately enough to be able to do that. Now, actually, it's turning out that even at a more sophisticated level, even when you're looking at things like general relativity, when you're looking at thermodynamics, there are similar questions about, can you prepare the universe precisely enough to make use of its enhanced computational capabilities if it had them? The answer, I think, is no. And I think that's a feature more of at least our sort of impression of our theory about ourselves as it is necessarily something just about physics. It's like, how would we prepare it? How would we do the experiment? How would we describe the experiment? Independent of what the actual physics has on offer. I don't think the physics has on offer those things, but even there's a problem. But in sort of tradition of theoretical physics, it's been calculus, and it's a giant calculus use case. The good news is that our models can absolutely use that stuff, but they have a different foundation, and they actually suggest and require a major generalization of calculus to really make the best progress with them. It's a question. What do I think about the academic community? Wow, that's a very general question. I have many friends who are academics. It's a funny business because I'm interested in, ideas. I'm interested in turning ideas into real things. I have spent some significant part of my life building essentially a machine for turning ideas into real things. It's a company, it's a whole ecosystem around the company, it's a bunch of tools I've built and so on. It's been hard work. I've spent a significant amount of time doing that. Maybe even I've had to have some talent in being able to do that. I don't think it's for everybody. And if your goal is to have sort of a life of ideas, there's some, how do you get to do that in the modern world? Well, academia is a pretty good place to do it. I think that, I've kind of led a life where I've never had a boss. The only jobs I've had are sort of professor-like jobs, and you don't really have a boss if you're a professor. You kind of have, there's the university administration, but mostly you get to do your own thing. And I think that's, I don't know how academia has evolved entirely in the 30-something years since I've not been involved in it, but it's a sort of a good place to have a life of ideas. Now, things happen. Like, for example, academia is big, and all these fields are big. And when things are big, they get a lot of institutional structure. And institutional structure is usually not good for the sort of individual, I want to have a big idea. The institutional structure is good when there is a job to do in making progress. I personally think one of the important roles of academia is the sort of the transfer of knowledge through the ages, so to speak. And I think sometimes modern academia loses sight of that idea, but that is from the 1200s when the universities were started. That is one of the great things that was achieved, was certain knowledge was passed down and successfully preserved by monasteries, universities, and so on. And that's a really important function, and not to be forgotten in sort of the operation of modern universities, I think. But I think that the mechanics of academia, it's big institutional structure. It has, it's not great on, there's a lot of kind of bad human behavior, I would say, that can happen in academia, because it's not a very well, it's not something where, things are very intangible. I mean, it's like, when one's dealing with companies and things, it's pretty well defined. There's NDAs, there's this, there's that, there's, it's sort of, there's a set of expectations that are pretty well defined. In academia, those things, at least in my experience in the past, were much less well defined, and that led to a lot more kind of human angst than I think happens in places where it's better defined up front. I mean, I think it's also, when it comes to things like the whole ecosystem around, peer-reviewed journals and things like that, it's a mess, in my opinion. It's a mess. I mean, it depends what one's trying to achieve. I think when there is a well-developed field of science and there's just a heck of a lot of work to do in making forward progress in that field, then it's a big industrial thing, and it needs a lot of people, needs a lot of structure, and there are things that you put in place to make that structure move forward smoothly, and that's fine. I personally am more interested in the sort of the big ideas story, and that structure is often, against sort of the emergence of big ideas. Now, I think that in academia, well, for example, in the peer review business, I cannot, the idea of anonymous peer review is weird to me. Back when I used to do that stuff, towards the end at least, I got the idea, actually, okay, I'll tell the story. There's a person, unfortunately, no longer alive, named Bob Krechnan, who was the last postdoc who had worked with Albert Einstein, okay? And he gave me an idea that I started using, which was, he said, I'll only do peer review if I sign my reviews. He said, I'm going to take responsibility for what I say. If I say the paper's nonsense, I'm going to say the paper's nonsense. And, the authors can come and complain, you got it wrong, et cetera, et cetera, et cetera. But I'm confident enough that if I say it's nonsense, I'm going to stand up for the fact that I said it's nonsense. And, if I say it's great, that's fine too. And maybe the authors can send me a thank you note if they appreciate, what I had to say, or maybe I'll have some suggestion. If I have some suggestion, maybe the authors will be grateful for that and so on. But, sign the review. And why wouldn't you sign the review? What's the reason not to do it? Do you not believe in what you're saying? So then I had the interesting experience of I would tell journals, look, I'll do this review. I haven't done them for years, but I'll do this review, but I'm going to sign the review. And they would say, oh, no, you can't do the review then. I say, why not? What's the problem? And so that was a sort of a strange thing. In this journal that I started, I haven't been involved in its operation for many, many years now, but Complex Systems, in the early years, I used to be at least aware of what was happening in the kind of front lines of the peer review and so on for that journal. And one of the very disappointing things that I saw there was the level of sort of politics of peer reviewing. And, it's kind of like, it's, the ultra cynical view of peer review is, if the paper, it's a natural selection theory of peer review, if the paper refers well to me and my friends, accept. If the paper doesn't, then reject. And that is a pretty good first level model for, I have to tell you, based on my observations from years ago, so, maybe it's changed. I can't imagine it's gotten better. It's a good first level model for what, happens a lot of the time in the front lines of that. And I think the thing, and that's not, what on earth is that doing for anybody? That's not advancing kind of the intellectual cause. And I think what we discovered back in the day, I don't know what's happened now, but we discovered that sort of people early in their careers who don't have sort of a big axe to grind, and people late in their careers who don't have a big axe to grind, those are the best sort of reviewers for papers and so on, because they're not going to just throw in the, they're not going to primarily be just, promoting their own cause there. But, I'm afraid that the sort of corruption of peer review is, I don't think it's a good system. And I think that the notion of sort of people who stand up for saying, yes, I think this is sensible, and I'm putting my reputation on the line to say it's sensible, that makes sense. I think the idea that there's sort of hidden, a hidden state where something wonderful is going to happen, well, it isn't wonderful. It's actually usually quite corrupt, and it's also usually much lazier than you can possibly imagine. I mean, people would say sometimes, when Mathematica first came out, they would say, how can I trust that you've got this algorithm right or whatever else? Even when they could see the code for it or whatever, they could say, how would I trust that? Well, I would much prefer to base my next work on a peer-reviewed, paper somewhere. It's like, okay, good luck with that. Do you imagine that the peer review process is as good as software quality assurance? I'll take the million automated tests that we've been able to run with QA, and the sort of carefully organized bug tracking system. I'll take that any day over the peer reviewer who was supposed to read the paper but actually didn't do it very carefully. Now, there certainly are people who do a really careful job, and I've been really pleased that with our physics project, that we've been getting a lot of typos sent in. We did this project very fast, so I'm always a little embarrassed that there are typos, but it's also a good sign when people are sending in typos, because it means they're really reading stuff. And when people have been asking, very detailed questions and very, very sensible questions, why does it do this? Why does it do that? And so on. That's a depth of reading that is really nice to see. And I'm, we're sort of gradually, it'll be amusing to see, as I'm going to do the exercise. I haven't published an academic paper since 1986, but I'm going to do that with this big 450-page object. And it'll be kind of interesting to see, what additional value, if any, there is in that process. But I think that the, kind of opening out everything we're doing is sort of the ultimate kind of, is the ultimate way to kind of be able to assess and understand what's happening. There's not a lot of hidden state. This is very much non-hidden, explicit state. I suppose that's what I get for being a language designer, interested in making sure that there isn't hidden state that users don't understand. I'm applying that to this project as well. It's funny that in the end people only have a few ideas. But so that's I would say that, okay, the other issue with academia, which I have to point out, is because it's big, there is a lot of departmentalization. That is, people say, well, what is that project? Is it, pick one, something that should go into the condensed matter theory group? Should it go into the gravitation, the experimental gravity group? Should it go into the theoretical computer science, computational complexity and cryptography group? In other words, it's been micro-sliced. Why does that happen? Well, it happens because when you have a lot of people doing stuff, it's sort of inevitable that you have to do that as a way of organizing things. Like, my company, it has departments, it has groups. We have lots of projects that go across groups. Those are pretty complicated to manage. We have a whole project management infrastructure that's all about managing projects that cross over groups. I don't think there's any such infrastructure in something like academia, or in the funding of academia, for example. But anyway, you end up with these things where you have these silos that inevitably develop. And they develop in another way as well, which is that ultimately, money matters in getting things done in academia. Ultimately, it's people have to get paid. To some extent in academia, the sort of ecosystem involves your teaching, and that's the way you get paid. But people have, research grants and so on, and they fight for those grants. And the question is, how do you figure out what grants to give? And so, I've talked to people who are involved in managing that process in the US in particular, and in some other countries as well. It's like, how do you figure this out? You've got a certain amount of money, some number of billions of dollars, and you're going to give that out for basic research. Why are you doing that? Why do you even fund basic research at all? What's the point? Why would you fund studying the fundamental theory of physics? Why would you do that? It's an interesting question. Because, society has lots of things to spend money on, particularly at a time like this. Why is basic research up there on the list? And I think there are several answers. There are some very pragmatic answers that have to do with kind of human resource development, that basic research is kind of the thing that lets people exercise kind of their sort of intellectual prowess and helps you develop a group of people where, when there is an issue, like a nasty virus comes and attacks the world, basic research kinds of things, and developing their skills there. That's a very pragmatic answer. I think that there are answers that are like for the pride of the species, so to speak. Like it's, we feel pretty good. People felt pretty good about the moon landings, for example, as, look what we managed to do as a species. I think there are sort of aspects of basic research where we can say that again. Even things like finding the fundamental theory of physics, it's kind of a pride for the species type thing if we can all do this. I think that there is if one's a little bit more cynical about the whole thing, there is there are questions for a country, like we do basic research because we want to be ahead of all the other countries. We want to win relative to the other countries in the world. And that's, basic research certainly has its trickle down to technology, to military uses, to other kinds of uses. and that can be an important thing for a country by country kind of thing to do. Another thing, realistically, is, in a sort of standard democratic country, there's a certain amount of scientists represent some block of the voting public, so to speak, and there's a certain amount of money that's out there that you can say, well, there's that group. The government has money. It's going to give some money to that group because that's part of the democracy, so to speak. And that's another point of view. I have to admit, I've asked this question at the U.S. National Science Foundation, for example. I happened to ask that question once in a meeting that I had with a bunch of their upper management. It was kind of interesting to see the answers to that. But I think the real answer in the end is here's when basic research makes, historically, if you look at where basic research has been done, for example, Bell Labs did a lot of important basic research. IBM in its day did a lot of important basic research. I think that basically basic research monopolies are a really good place for basic research to get done. Now, there are lots of reasons why monopolies might be bad, but one of the things that's good about them is it's a good place to get basic research done, because when there is a monopoly, and one might argue that, for example, the US at an economic level, because it's sort of, at this point in history, the dominant economic power, sort of if something comes about that is good for the economy, it's good for the US. And so if you're in a position like that, it makes sense to fund basic research. I mean, I know even in our tiny corner of the world of things about mathematical computation and things like this, we do basic research in those areas because we are likely to be the main beneficiary of that. And it's, that's one of the pragmatic reasons to do basic research, is that the ecosystem that is around what you're doing is such that you have the main distribution channel. If some great economic thing happens, you're the main country, for example, that can take advantage of that. Now, maybe that's sounds a little bit jaded and cynical, but I think that that's a thing worth realizing historically, that there may be downsides to monopoly, but one of the upsides is it's a place where it makes sense to do basic research. In a case where there's, basic research by its definition is not something where, it's not something that's going to have a payoff here and now, so to speak. It's something that's for the future and potentially something that could take a long time to pay off. Anyway, long diatribe or something about that. I think that, it'll be interesting to see in the current physics project. I would say that the initial indications are really very nice in terms of the response of the academic community to it. I think they've been very warm and positive. So far as I've seen, maybe there's stuff I'm not looking at. I wouldn't tend to look at these things. If you say to people in a field that has been in sort of slow progression for a long time, you say, gosh, there's something new and exciting, you can take off in a speedboat type thing. I don't expect you'll see that in a week. I would hope in not too long, we'll start seeing papers kind of connecting the things we're doing to things that people have already done in areas of mathematical physics. Okay, so question here: how does the process of doing science today differ from what happened in Newton's day? What's better or worse? That's an interesting question. It's funny. I happened to get, I think it's some little company I happened to have this on my desk. I got this thing. I can show it. This is a facsimile of Newton's college notebook, and it's kind of a cool thing, actually. It has his kind of notes that he made when he was in college. It's actually notable for the fact I had no idea they taught so much. There's a bunch of math, but there's also a bunch of music theory in here, which I had no idea they were teaching in Cambridge in the 1660s or whatever. But anyway, so it just so happens I had this on my desk. But I thought it was a cool artifact. I just got it. I think that Newton worked kind of mostly by himself. I think he wasn't he's not exactly the most collaborative of people, from what I gather. I think, though, there were people at the time who had students, and they, had the equivalent of graduate students and so on. I think that in Newton's time, it's kind of funny. What we can see from the history, the amount of skullduggery in academia at the time was very dramatic. It was full of, committees, secret committees that would figure out who had invented calculus, and they were stacked with all kinds of sort of shocking, corrupt elements. Or there were things where, people were putting up, these competitions to prove who was the greatest, whatever. And there was the skullduggery was, at least from our vantage point, 300 years later in history, looked like it was more out in the open, but it was vicious. It's probably still vicious today. It's just people don't know it as much. But and Newton, things he was worried about. Would he get credit for this? Would he, should he expose that, and so on and so on and so on. I would say that I think Newton would have had a good time with Mathematica. There were tools that he didn't have. I mean, he was just doing his pencil and paper thing, and he had to, when he did a chemistry experiment or an alchemy experiment, more what he was doing, he had to build the apparatus himself. He had to it wasn't maybe one does that at the front lines of science today too. I mean, I would say, look, there were differences. I mean, for example, the shorter human, lifespan was a big difference. Today, it's, somebody can be an academic for 50, 60 years and can carry the ideas that they have for that period of time. Newton was lucky. He lived into his 80s. And some of his work, he was doing his important work in some cases in his 40s and older. Not everybody was lucky enough to live that long in those days. I think the longer human lifespan has changed both for the better and for the worse, perhaps, in the sense that it's possible to do, to build up a larger portfolio of knowledge and experience. Certainly the things I'm trying to do right now, I couldn't have done many of them, much earlier in my life. And I think that, that's the good news. The bad news is, the ultra cynic has the quote, scientific progress is measured in a succession of funerals, right? That's a very, very, very cynical statement. But there is a certain sense in which people tend to get a certain way of thinking, and they can get very locked into that way of thinking. And if they're doing it for 50 years, and it's kind of like, no, you can't change, you can't do anything new, and we're going to do this for the rest of our career, that's a bit of a downer. Now, another thing to say about Newton's time, in the area that he was working in, there were a small number of people. In the area of figuring out, celestial mechanics or something, I don't know how many people there were in the world working on it, a few tens of people probably. It was small. Of course, there are plenty of areas of science today that are small, but an area that's hundreds of years old is not small anymore. If it's gotten traction, it's very big. It's tens of thousands, hundreds of thousands of people working on it, and it's a very different feeling working in a field that has 100,000 people working in it than working in a field where there's just 10 people working on it, and where you can know all of them. And I think that's that is a difference, but there are many more fields of science that work that way today than in Newton's day. But it's an interesting question. I mean, I don't know. In some ways, it's very similar. I mean, it's like you're figuring stuff out, you're writing stuff down, you're trying to explain it to people. People understand, they don't understand. You keep going. You have to have sort of the confidence to decide you're going to try and do something. It's the same story, and it's very much a human story. I think, well, one thing that changed in Newton's time, okay, this is an interesting thing. Journals were invented in Newton's time. Newton was able to publish some of the things he did in journals. The Proceedings of the Royal Society was created right around Newton's time. And that was a new thing. Now, if you read those early journal articles, they read like blog posts. They were basically, the kind of thing that I've written in, sort of informal blog posts. That's like the journals of the 1600s. The modern, we will show this, reference 7, et cetera, et cetera, et cetera. of modern kind of almost desiccated academic communication, that is a phenomenon of modern times. And I think that the some of the sort of in some ways it's rather charming reading the old proceedings of the Royal Society. I went up this hill and I noticed that at dawn there was a green flash or something. It's very much the in modern times you can translate that into modern. A measurement was made at when the sun was at azimuth such and such, altitude such and such of this, and we observed the following whatever. You can translate the sort of the blog-like descriptions of what were in the early journals. I think it's kind of nice to have the human side of it explained. I think it's one of the things that's been lost in some ways. It's coming back a little bit. Some people are doing more of it. To be able to say, why did you do this? What was the story around doing this? I think that I sometimes make fun of some kinds of mathematics papers by saying, every paper begins, let F be a field. Okay, why are we looking at F? Why do we care about F? Well, the paper comes to an end and it never explains that. Now, there's a certain perfection in that. There's a certain kind of plug compatibility. It doesn't matter why we were looking at F. It's still true what we said in the paper. But still, at a human level, I think we humans communicate better when we're kind of telling stories to each other. And it's better if you can kind of tell a human story around kind of why you're doing something, what it means, how important you think it is. One of the things that was significant to me in my New Kind of Science book, one of the things that I discovered about explaining what I'd done to people was if I'd said, well, I discovered this thing in cellular automata and it's this phenomenon, blah, 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 people would sort of say, okay, so it fits into the renormalization group and it fits into this, it fits into that, blah, 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 blah. And I kept on saying, no, it doesn't. It's something new. It's something really different. And you don't have an intuition for it. At least I certainly didn't have an intuition for it. It's something you haven't seen before. And that idea that it's something you haven't seen before, presetting this level of it's something, significantly different than what you've seen before is very important for having people understand something. Now, for better or worse, that's why I called my book A New Kind of Science rather than, an incremental contribution to the theory of complexity or whatever else, because I discovered that in trying to explain these things, the first thing you have to say is, this is a big step. And, it may be a big step you care about, it may be a big step you don't care about, but it's certainly a big step in terms of it's really different from the intuition you had before. And so that's that's part of the sort of meta communication of the science. And by the way, I think in terms of the science we're doing on this fundamental theory of physics, this is the live streaming and the kinds of things we're doing around that. That is a lot of meta science. It's a lot of kind of explaining what the point is and trying to, even what I'm trying to do here today is sort of explaining the ambient story of what's going on with the science, in addition to the actual raw kind of mechanics and technical aspects of the science. All right, let's take a look here. We've got a whole bunch of other things. Let me try and speed up a bit. Have I had any reaction from those who've worked on M theory? I am embarrassed to say that I know I have reactions from some of those physicists, and they're sitting in my mail unread at this point. So the answer is yes, but it's kind of like the unobserved phenomenon. And it's a quantum pure state still. It hasn't been observed, so I don't know. Let's see. Are you worried by the opinion of other people regarding this project? No. I mean, this is one of the things that comes with the territory of trying to do sort of big, bold projects. If you are always looking over your shoulder at what do the other people think, you don't get to do these projects. Essentially, every important project I've ever done in my life, people said it was a crazy project. And, I happened to run into the chap who discovered the solar wind. His name is Parker. He's had a spacecraft named after him. He's quite old now. But I asked him, last year actually, I asked him, there were people who had said the solar wind is impossible, right? Okay, when artificial satellites started getting flown, well, people discovered the solar wind. I said, what happened to the people who said that the solar wind was impossible? you know, what did they do? You know, they go on working on astrophysics and go on talking about stellar structure and so on. He said essentially all of them, for the rest of their careers, still said the solar wind was impossible, even though it had been, you know, observed with complete clarity by satellites and such like. So it's you know, I think the what do other people think question, it's you know, for me, the more important question to me personally, and there's just a pure personal thing, I won't claim it has any profound sort of ramifications, is I like the idea that people are having fun with ideas that I have, or fun with things that I built. For me, that's a sort of the communication of fulfillment is something that, for me personally, for whatever reason, the way that I'm built, it happens to be something significant to me. Much more so than whether I think people are endorsing what I've done, and people say, you know, I mean, it's nice when people say good job, I appreciate it. But I'm more interested in them saying good job because they're having a good time studying it than because they're saying, hey, you were clever, you did a good thing. I mean, I you know, perhaps it's I don't know whether it's an imperfection or a good feature, but I just don't care that much. And in you know, and in fact, I have sort of, I really don't, you know, I don't pay attention. And that has the feature that, you know, whenever somebody would say something like, oh, this was completely crazy, it completely misunderstood this, it's like, that's kind of annoying, because it's like the person just didn't understand, they didn't bother. It's like, look, I put all this effort into this thing and you didn't even bother to read. You know, you're like, oh, you don't have references, this is shocking and anti-academic. Go look at the end of the document, you'll find them there. But, you know, it's kind of annoying when people say things like that. I think the one thing about the reactions to my New Kind of Science book that I was annoyed by was the fact that people said, oh, you haven't sort of given reference to other people and so on in the book. Well, you know, I had the theory that the internet was mature enough that if I, you know, that given keywords and names, you could do a much better job of actually finding papers, if that's what you wanted to do, than I could do by giving you a list of 1,000 papers, or actually it'd be more like 10,000. But what I did do, and I spent a huge amount of effort on, was writing historical notes in the back of the book about what the actual history of the ideas was. And I think everybody who would challenge me on this would say, you know, I said, did you read the notes? I said, well, yes, I did read them. They were really good, actually. It's like, okay, what's your problem? You know, I really put a great deal of effort into those notes, and I did a lot of, you know, original interviews with people. For example, I did one very interesting one with John Conway, who unfortunately died recently. Actually, I have a recording of that interview that's pretty interesting that maybe we'll put online at some point. It was done many years ago in the 1990s, about some of his thinking around some of the work he did, particularly on things like Game of Life and so on. Not quite what the public knows about it, actually, but I tried to represent that accurately in the notes that I wrote in the NKS book. And, you know, those notes essentially fueled what became like the book I wrote called Idea Makers, which is a kind of historical biographies book. And so, you know, I've taken that history rather seriously. And now, you know, I have to say in this physics project, you know, I put a bunch of references into the main paper that I've written about this, and I think they're good and relevant references. But I have to say, in getting this project done, I haven't done all the history work. So if you start asking me what precisely is the chain that leads from John Wheeler and his talking about pre-geometry to causal dynamical triangulations to, you know, ER equals EPR, I can't tell you that whole chain of history. I mean, I don't think it's super relevant to the physics we're doing. It's like, I did the academic thing, I put a bunch of references to all these things, and it's like, okay, go figure out the history if you want. But I think it's actually interesting to know what the chain of connections between these things is, and I haven't explored that. And it's I would enjoy doing it, but it's kind of a thing that takes time, and I've been spending my time actually trying to figure out the physics. Let's see. Are there critics to your approach to doing science by my science colleagues? Actually, that's an interesting question. I haven't seen anybody saying it's shocking to do science in live streams yet. But I haven't been looking at these things, so they may have said that. I don't think it should be shocking. Why would it be shocking? I mean, it's kind of like, people may find it, may find it really dull to try and see things get worked out. That's, we're not telling anybody they have to tune in, so to speak. But I think providing it is kind of cool. What's the opinion of my family in terms of doing live science? I do not know. I pretty much guarantee that none of them are watching this, for example, but that doesn't necessarily tell you anything. I know my son Christopher has been on a few live streams that we've done, for example, some about the epidemic and so on. I think I'm hoping he's going to join a live stream tomorrow, because I think he has some interesting things to say. But he's probably the only member of my family who's actually been involved in these live streams. Let's see, there's a question here from Jimmy, a little bit more philosophical question. What's the difference between a computational model or a simulation of all of physics and a foundational theory of physics based on computation? Let me not get into that in too much detail, but I think that's actually a very interesting question. I mean, I could say, here's a rule, go run it 10 to the 400 times and you'll get our universe. And that's a very non-useful thing to say in a sense. And then I could say something where I think a foundation of theory of physics based on computation is about sort of bringing what happens in the physical world to the point where we humans can understand it through the medium of computation. That's really what that's about, as opposed to just saying, here's the rule, just trust me on that, go run it, which is more like the I'll just simulate everything. Okay, question here. Will the project lectures at the summer school be live streamed? Good question. Maybe we should do that. I think sometimes when we get to the end of the summer school and people are presenting their projects, the summer school is usually, for many people who come, has been their first experience of doing original research. I think it's an important one for people, and I think people have a great time, but they're sometimes a bit nervous about presenting what they've done. And I'm not sure that live streaming it would be a positive in terms of people who are not used to giving presentations, but it's a good idea, and we should think about that. Maybe we'll just tell people, just ignore the camera. Let's see. Question from Eigen Tourist, good name. Models with multiple applications, are there ones that describe contagion patterns? There's actually a live stream we did about contact tracing. There's also some stuff about networks. Actually, my son Christopher did some posts about that that you can find if you go to our main website, wolfram.com. There's a thing at the top that is resources related to the pandemic, and you'll find some of that study there. Okay, there's a question from a wild techno that it says, isn't that just called math? I'm afraid we lost the referent for what the that responds to, so it's hard for me to respond to that. There's a question here from Plenumbra. Have theological or existential questions been much of the motivation for my research? Not really. I mean, I've been just like, find fundamental theory of physics. Kind of that's an objective. But then as I think about it, it's like, why this universe? Why not another? Why has this universe been actualized at all? These are questions that come up. Often I initially think there's going to be nothing scientific that can be said about that. But the big surprise has been some of these questions, we get something scientific to say about them. For example, the free will question, we have a lot of scientific things to say about that. Some questions in, for example, AI ethics and ethics in general, I think there are pieces to that where we can sort of box them, wall them in and say there's pieces where we just can't have anything to say from science because it really is just a reflection of human values, which aren't sort of defined by science. But I think it's been, I'm sort of interested in, become increasingly interested in what is just a reflection of human values and what is something for which there can be a perfect scientific theory. And where's the boundary between those things? And that has been interesting to me. I think that I rather pragmatic. I mean, in a sense, it helps to have a day job that involves actually building technology and things that it makes one rather grounded in what can I actually deliver, so to speak. And so I would say that the motivation for things I do tends to come from the pragmatic side, although I'm certainly not, particularly when I think that sort of reflects on some theological or existential question, it's something that I like to not shy away from. Actually, I've been considering doing a live stream here with a friend of mine who's a theologian, talking about some of the sort of what theological ideas kind of give you sort of ways to think about sort of the meta notion of fundamental theories of physics and so on, and other things actually. And there are questions in AI ethics that have been really thought about in that sphere a bunch in the past. So that may be something coming in the next few weeks. There's a question here: how do you stay motivated in your field of work? You know, I stay motivated because I'm really interested in the stuff that I'm doing. So it's kind of as simple as that. And if I'm really not interested, I don't do it. You know, I have found though that, you know, sometimes there are technological questions that come up that are of practical importance for the products we're delivering, and it's like, oh, can you really you know, be motivated to that? I found that essentially any question, if I try and really drill in and really understand it in detail, if the answer isn't obvious, then the question is interesting, almost by definition. Now, there are times, you know, you talk about motivation, like, for example, what did I spend yesterday evening doing? Well, I spent a large chunk of it doing consistency, putting in consistency in the index for the book version of the physics project, okay? And I admit that that was a slightly challenging to motivate kind of thing. You know, I think I am, you know, I'm kind of fairly diligent, and so that that, you know, I'm like, once I've got through the A's, I'm going to get to the Z's. But that process, you know, you might say, why couldn't somebody else do that? The real reason is making indices, which maybe is an almost lost art, is something where you kind of have to understand the content quite well to make a good index. And it's something where, yeah, sure, somebody else could try and do it, but honestly, it would take them a long time. And I think they would, you know, I would end up saying, why did you index this? Why didn't you index that? Oh, they didn't really understand that was the key idea on that page. This page is really only making a you know, a partial comment on that. You don't really need to put it in the index. But the thing I was doing yesterday was kind of harmonizing different parts of the index. And that's pretty, you know, it requires a lot of concentration, but it is not, you know, it probably could be done by maybe the more, I don't know, reptilian part of my brain, so to speak, or something. I don't know what. You know, basically, the way I stay motivated is because I do stuff I really like doing. Now, you know, I have been known to procrastinate, and particularly that happens, the worst case for me is when I start doing a project and I have to stop, and then I have to restart it. And I'm really bad at that restarting. And it takes me really a lot of that. That's the thing that requires kind of the most personal kind of mental force, so to speak, to restart these things when they've been stopped. Because I feel like, you know, so much state has been lost. And I kind of know when we do technology development and architecture and so on, I kind of have studied, and people who work with me have studied kind of the decay time of my memory, so to speak. It's kind of like, if a week goes by, I can still remember, I can still be right back where we were before, you know, thinking about the things the way we were thinking about them. If a month goes by, I can't do that anymore. And I'm having to restart, and there's sort of a lot of wasted time there, and I kind of resent that. Let's see, okay. There's a question here from Zenny. Why is it that physicists are hired at hedge funds typically? You know, I did a thing a few years ago. The woman who was the chairperson of the physics department at Harvard, asked me would I come and give a talk for the graduate students there about what physicists do when they graduate with PhDs. And so I'm like, okay. sure, I'll do that. And she said, you'll recruit some people there, good thing to do. So I was like, sure, why not? So I give this talk and I start off by saying, do you guys know what sort of happens to physicists? What do they end up doing? And so it's 60, 70 people there or something. And it was terrible. There was this terrible sort of silence of, people were doing their PhDs in physics and they were like, we don't really know. It's kind of like it's off the edge of the world type thing. Now, this was some number of years ago. It was a terrible experience because it's like, and then somebody sort of said, well, I think some of them go to Wall Street. I think some of them become programmers. And it's like, yeah, those are things that happen. Now, physics is a really good export field. It has been historically the best export field. People learn physics and then they go off and do all kinds of things. I mean, for me, physics, the modus operandi of physics is just use analytical skills to get an answer, whatever it takes. And that's a very good kind of underlying thing to learn. And in fact, in the past, physicists, populated molecular biology, they populated, mathematical finance, financial engineering, they populated a lot of logistics kinds of things, they populated a lot of different areas because of that attitude. We're going to use analytic skills, but we're just going to get to the answer, whatever it takes. And that's a great kind of way of thinking about things. And historically, people learn physics, they get PhDs in physics, they study physics, and then they go off and apply that mode of thinking to a lot of other things, and it's great. I would say in modern times, computer science has started to be another important export field that has its own kind of, it's write a program to get something done. And I think, but still, that's something that happens in physics. Now, many good friends of mine run hedge funds. Hedge funds are very big users of our technology, and hedge funds, a lot of smart people at them, very smart people. Not my kind of thing particularly. I actually considered when I was working on the NKS book, I considered for a while. This was in the early to mid 90s. I considered taking a vacation and basically doing what would now be called a hedge fund, doing quantitative finance just for fun. Because I thought, I could use a bunch of methods, and I got as far as sort of investigating what it would take, and I was like, this is not for me. I just don't care. These are interesting problems for the sake of problem solving, but for me, I'm interested in building things that can be built on top of, and I think that a lot of the, let's figure out how to, beat the market today. And whatever we figure out, eventually the market will stop us using that method to beat the market, and we'll have to come up with something different tomorrow. Just doesn't happen to appeal to my personal set of intellectual objectives. But it's a very, for people who are interested in solving problems, they're really interesting problems, and it's a very, 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 well, I was going to say rich area, but that's too literally true. Let's see, is someone saying Roger Penrose and Rudy Rooker are science heroes, and I think both of those people are great too. In fact, Rudy and I did a really fun podcast together. When was it? Sometime last year, and maybe we'll do another one of those. It's really, really interesting, and I'm always keen. Rudy is kind of a his background is in mathematical logic and, New Gödel and people like that. But he's been writing science fiction books for a lot of his life. He wrote actually he's written science fact books. He actually wrote a nice book that's a follow-on to the NKS book, where he's kind of exploring sort of the intellectual consequences of new kind of science, together with sort of the way that it fuels stories of a science fiction kind. And I've been sort of poking at Rudy a little bit last few weeks of okay, we've got the science, think about it in your kind of way of thinking about things, where you're not, held down by the science fact, but you can kind of go and say, what does this mean sort of out in the more infinite universe of science fiction. Roger Penrose, I'm hoping will be chatting with him soon, actually, about this, because I have to say, of all people who have sort of worked on fundamental physics, the kinds of both specific ideas and prejudices he has had about how physics works are the most aligned with what we're doing of anybody, I think, over a very long period of time, both in terms of his idea of spin networks and in his terms of idea of twistor theory. And now Roger has had a bunch of other ideas about non-computability in physics that I don't believe in, but it's I think okay, I have to tell one Roger Penrose story, which I hope people won't be too upset with me telling. But this was back in the early 90s. Well, actually, I'll tell you two stories. So first of all, when I was an undergraduate in Oxford, I went to some graduate class that Roger Penrose was teaching about general relativity, and I actually just found the notes that I made in that class just last week, a week before last, actually. It was kind of fun to see that that was when I learned a bunch of things about general relativity that I've now been able to use in this project. And it's like the Roger Penrose was explaining this is how it works, and I think I can say, okay, I know why that works that way now, which is really cool. But anyway, the thing that was really fun with that class was that wasn't a very large number of students in it, but it was Roger Penrose did the sort of, in some ways, the perfect British eccentric professor thing of, he'd do some thing on a blackboard, he'd start at one corner of the blackboard, he'd try and do some derivation, and then at the end of an hour, he'd get to the other end of the blackboard and he'd look very kind of quizzically and say, that's the wrong answer. And kind of the exercise, which I think I was the main one who was doing, was, okay, what went wrong in this whole hour-long derivation? But it was very charming that he would get to the end and he would just be like a little embarrassed, and it's like, oops, we got the wrong answer. But I thought it was quite educational, actually, and very charming. But then many years later, another Roger Penrose story that I have to tell because it's just fun. So Roger Penrose had written his book, Emperor's New Mind, that was kind of about sort of the limitations of computers. I don't happen to agree with the particular conclusions he came to there, but it was, and there was an article in Time magazine, I think, and I think its headline was, Roger Penrose says computers are all dummies, okay? So I happened to have just seen this article, and it was in the early days. It must have been earlier than 1991. It must have been maybe 1989, just after Mathematica came out. And those were days when I would still like leaf through there used to be physical registration cards of users of Mathematica. And, I'd leaf through finding out, who were some of our users, what kinds of things people are doing with it, because we'd ask them, what are you going to do with it? And I was just really amused. I had this copy of Time magazine right there with this article. I was just on the page with the article from Roger Penrose saying, computers are all dummies. And as I leafed through the registration cards, there I got to Roger Penrose's registration card for Mathematica. So I was happy that even though, at some level he was saying computers are all dummies, he didn't think our way of using computers was so dumb after all. And he had his Mathematica, and I know he's been he and his wife actually, I think, have been users of our technology. But anyway, I think Roger Penrose has, I should say another thing, his idea of twistor space. We actually suspect that the multi-way causal graph, that the continuum limit of our multi-way causal graph may actually be a twistor space. So that would be a really cool connection with a bunch of mathematics that Roger Penrose has been doing since the 1960s. And I think Roger Penrose has his particular idea of spin networks, I think has a lot of very interesting mathematics. I think that it is rooted in kind of assuming 3+1 dimensional space-time, which I don't think is right. But I think that the idea of this kind of network structure is really interesting, and a bunch of mathematics that's come out around it is really interesting. And yes, he's one of my science heroes, or science and math heroes too. And so a question from Prasin: how important will multidisciplinary approaches be here? It's funny because a lot of what I do involves sort of pulling in ideas from different places. I think with this project, we're going to see pulling in ideas from distributed computing, pulling in ideas from mathematics. I don't know how much further afield it will go than that. I mean, it's always fun to realize in the history of science, 3 fields: economics, biology, and thermodynamics in physics. And the people who sort of were key people in those fields: Darwin, I guess Malthus, and Boltzmann. And it's kind of fun to realize that the thermodynamics, Boltzmann's theory of thermodynamics was, I'm trying to now get my history right. The order was really funny because Boltzmann was derivative on economics. Boltzmann in physics was derivative on economics. And I think both have been derivative. Is that the right history? 1859 was Darwin, 1870 was Boltzmann. Malthus, I don't know. Sorry, I don't know that history well enough. Sometime right around then. But maybe it went biology, economics, physics, which is kind of not the sequence you might expect. So it's hard to know where ideas will come from. But I think primarily, probably mathematics, computer science, and physics right now. Yeah, Brian is noting that GPS is an everyday application of general relativity, but with the proviso that I also mentioned here. Okay, I'm gonna scroll down. I gather people were interested by my little stories about Roger Penrose and people like that. I'd be happy doing these things one day because I've known a lot of scientists, and sometimes I'll write obituary pieces about them. All right, I'll tell you if you want to know stories. Let me tell you a couple of stories about John Conway, who sadly passed away last week from this nasty virus. I think the thing about John Conway, he was interested in a lot of kind of questions about sort of mathematics and computation, quite similar to questions I've been interested in. We had a very complicated relationship because I think ultimately because our motivations were just utterly different. I mean, the questions we were interested in, the actual, let me study a system of fractions that can emulate a universal computer, let me do this and that and the other, those are some of the same questions. But I was interested in those as a way to kind of build up this intellectual area of science. I mean, I think John Conway's interest was very, very different from that. And I'll give you an example. The first time I met John Conway was a conference in the south of France in the early, probably 1982, 3, something like around that time. And we were at this lunch, and there were a bunch of kind of well-known mathematicians sitting around. And, John Conway was there asking people when their birthday was, and then telling them, oh, you were born on a Thursday, or whatever else. And I was like trying desperately to steer this conversation to something that was more about sort of the content of mathematics, so to speak, and less about. And eventually, I have to say I was younger and brasher in those times, and eventually I just completely lost it and just said, "Look, stop talking about this. This is stupid." And so then John Conway and I went on this long walk. It was very, and the first question he asked me was, why was that stupid? Weren't people impressed? And I said, no, that's a sort of a math piece of trickery. These are all people who are sophisticated mathematicians. Everybody at that table knows that they could have figured out how to do this, but they don't care. But for him, kind of the act of sort of being able to figure out, how to do that math very fast, that was something that seemed significant to him. Now, one of the things that I was interested in was, how did the game of life come to be? The game of life cellular automaton. It was 1968, 1967. And so and John Conway always sort of said, oh, it's a game, I was just playing around, et cetera, et cetera, et cetera. So I when I was working on the history notes for the New Kind of Science book, I said, I had a phone conversation with him. In fact, that's the one I think we have a record of, in which I said, I want you to tell me, how did this really happen? What were you really thinking about? So it took like half an hour. And eventually he said, well, I'd just been hired as a logic professor. I didn't really know much about logic. I wanted to figure out something interesting about logic. And in fact, I wanted to figure out an enumeration of the recursive functions. And I wanted to find sort of the simplest way to enumerate recursive functions. And I knew about stuff that Ulam had done about cellular automata and so on. And so I was kind of idealizing that. And eventually I got to this thing that could be played on these Go boards that was the game of life. And I was like, why did you never tell anybody that? The fact that you got to the game of life by studying the enumeration of recursive functions is much more interesting than the fact that you got to it by, by kind of just playing this game and so on. And he's like, I don't get it. It seems much more impressive to have gotten to it by, and much more engaging to people that one had gotten to it through this game. But anyway, so, I think our interests were just very divergent in terms of sort of the intellectual objectives, in terms of sort of, my interest has always been to tie these ideas to sort of this big trunk of sort of intellectual development. And I think he always felt that, it's a cool idea. Let's put it out there in the world. People will have fun with it. And a lot of people have had fun with his ideas. And it's like, it doesn't have to be tied to a big trunk. I mean, it's just different things for different people. I think that, I was, and I think some of the things, it's an interesting question. I've been sort of trying to research the true history of the game of life, because it's a fascinating example. It's a 50-year run where sort of engineering has been done and more sophisticated things have been built, but it's all at the level of pixels. And so it's a place where you can kind of study the meta trajectory of engineering without kind of having to know about the details of silicon and things. And so I wanted to study that. And we did a couple of years ago, we really tried to track down the people who discovered these different kind of configurations in the game of life and so on. It's actually a very interesting group of people. It's a very, and I don't know what it tells us about, for example, this physics project, because a group of people that range from the professional mathematicians to people who really weren't interested in math, to people who are very computer oriented, to people who even were discovering game of configurations with pencil and paper, which is kind of a remarkable thing to be able to do. And I think that it's a little bit like what you see in something like the game of chess, where you see this wide spectrum of different kinds of people in different walks of life, different situations and so on, all kind of coming together in the case of this game. And I think the same thing we saw when we kind of peeled back the covers of who had discovered the things that have driven kind of the sort of this weird kind of engineering in the game of life. And I think it's a sort of interesting lesson in what can be done by people with just very different backgrounds. And we discovered when we talked to them that they didn't know, they knew nothing about these other people. We'd asked them, what do you know about so-and-so? Oh, I think he was a systems programmer for whatever, maybe. And it turned out they knew nothing in most cases about what some of the other people involved in the enterprise have been doing. People are asking about inviting other people into live streams like Roger Penrose. Yes, we'd love to do that. And David Deutsch, I'm hoping, we've been in touch with several of these people. And yes, we by all means encourage them to join these live streams. I think sometimes people are a little nervous because they're not used to, particularly when the invitation is, come join one of these live streams and help us figure out a bunch of physics. It's kind of like, we don't do physics in real time. But I think I think we can talk them into it, so to speak, and I think it'll be really interesting. Oh, that's interesting. Apparently there's a podcast by Sean Carroll. Okay, well we were talking to Sean Carroll about other things, so that's okay. Let me just look at a couple of other things here. There's a question here from Lawrence. Do you think the physics project will eventually become commercial like Mathematica? Well, Mathematica was born as a project where we were building a product that we thought would be useful to people. I was sort of user number one, but fundamentally we were building something that we thought was going to be useful to people. My very first software project and product, SMP, I didn't originally imagine it as a commercial product, but I kind of was backed into that because that was kind of the way that made sense. People who are going to use it were going to pay for it, and that would pay for its future development and so on. And it's been an ecosystem that's worked really well for sort of long-term development. As far as this physics project is concerned, I don't have any idea how to commercialize this physics project. I think that when we were talking about this project and we were considering that question, we were like, gosh, well, we can sell swag. And I think that's I don't know how expensive this project will ultimately be to do. Fortunately, we've had some great offers of free, very large amounts of computer time and so on, which will be certainly very helpful. There's human time and human effort of people really concentrating on doing this. And they may do that as part of their day job, being working in a physics department or something. But there's a question of sort of how that really works. And I think it would be an ultimate irony, just as people think about funding, moon missions by selling the movie rights type of thing. It would be an ultimate irony if we find the fundamental theory of physics because, on the back of selling physics swag. We're hoping to make some physics swag. I think it'll be kind of fun. But the answer is I don't have, my point of view about the way things should work is, you want to set up an economic system where the people who are getting value are the people who are supporting the value that is being generated. That's my opinion. Certainly that isn't the way, some parts of the internet have worked. It's a very different thing with third-party advertiser type input and other kinds of things where, there are projects that get done where we don't make money from the software, but we make it up in selling the books, or we don't make money from the software, but we make it up in selling service and things like this. And where the motivation isn't particularly to make, in the case of delivering software, it isn't necessarily to make the best software. It might be to make the software that you can make the most money selling service on or something, which I think is not, I like this idea of having something where the value delivered is what's supporting the value that's being created. Now, in the case of a basic research project like the fundamental theory of physics, I think the value that's being created is deeply intangible, as I was mentioning earlier. And I think it's value that I think is, I'd like to think it's something that we as a sort of species can be proud of having done. And so, many people have said to me, you should run a Patreon thing for the fundamental theory of physics. And, maybe we should do that. Honestly, at this point, it's a question of how much we scale up the project and how much money we have to spend. From my point of view, the effort to raise the money is greater than the effort to just spend the money, so to speak. And it's not worth doing that. But as if we try to mount an effort that involves 50 people working on this for a significant amount of time, which it may take, then we have to kind of make a real model for how to do that, whether it's from philanthropy or something else. But I don't think we get to sell the fundamental theory of physics. I don't think that's I don't think that's the kind of thing in this world that can be sold. It's kind of fun in patent law. I know one of the exclusions from things you can patent is laws of nature. So I think that's kind of, even from the time of the origination of patent law, that was a thing people had thought of as being no, that doesn't make sense. There's no there's nothing like that comes about that way. All right, I think oh gosh, there are lots and lots of interesting questions here. Boy, you guys are going to force me to do another one of these live streams, aren't you? It's look, it's interesting. I honestly, it helps me think through my own thinking to do this, so I really appreciate that. comments about, there's some interesting comments here about universities like MIT trying to encourage interdisciplinary research. I mean, I have to say, by the time you're in the business of encouraging it, you already know that there's a problem. And I think that, there have been some places in academia which are quite small often, where there's a small group of people that come from different areas. And I think some of those have been really fertile and really worked well. But it's just this tendency of everything becomes bigger, and so it sizes out. And then what you try and do is you make the meta silo, which is the silo that is the silo that connects these two existing silos. But the ultimate meta silo of let's put everybody together, it doesn't really work because it's too big. And also, one of the things that's happened in recent years, back in the 1980s, there was never a conference that involved people from many different fields. It was like there was a physics conference, there was a mathematics conference, there was a biology conference, but it was sort of not really a thing that there were these sort of mixer conferences. I remember the MacArthur Foundation. I happened to go to some early get-togethers that they had for their early sort of fellows, and that they've continued to have them now. But what was really interesting about those was that was a random group of people who happened to have these fellowships, and who, the MacArthur Foundation decided were doing interesting things. And, I met novelists and, people in all kinds of different areas of science, geologists, and many of those people I've stayed friends with forever. It was, that was sort of for me, one of the first kind of really mixer type situations. Those have become much more common in recent years, of sort of mixer conferences where you bring together people from different fields. And I think it can be very valuable. Unfortunately, in areas like fundamental physics, because there is quite a lot of technical knowledge there, it's much harder. I don't really think, if one had a conference about, fundamental physics and you brought in molecular biologists, I don't think that would be until we make more of a bridge, that is not going to be an interesting conversation, just because the technical stuff to say about fundamental physics is sufficiently tall that it doesn't really connect to maybe we can talk about the modeling, but that's about the level of it. So somebody's commenting, the problem with getting grants is you basically need to have already done everything and achieved the results. Yeah, I don't know, that ecosystem is really weird. I mean, I've never been in the position of doing that. So in my time in academia, I was always was lucky enough to work in places like the Institute for Advanced Study in Princeton that didn't work. Maybe does now, I don't know. But in those days, it was funded by an endowment that originally came from, I guess, the precursor of the Macy's department stores was the original source of the endowment for the Institute for Advanced Study. But the thing that one of the things that I know is kind of an unfortunate feature is, let's say there's a pot of money, $100 million for some program. People are going to spend a bunch of money writing the proposals, basically, to get that money. And it's far from obvious that less money is spent writing the proposals than is gotten from that pot of money. And so that ends up being a kind of it's sort of a high risk thing where the winner is taking, it's kind of a weird sort of setup. And I don't know, how can one do it better? People have asked me this, and I've thought about it a bit. How can you do better at kind of figuring out sort of how to fund and move forward science? One thing that feels very, doesn't feel like it's a thing of modern times, but I'll say it anyway, is, at some level you have to bet on people. I mean, I find it a little bit weird that you'll find people who've done a bunch of, they've achieved a very high level of success and achievement in some particular area of science, for example, and then they'll choose to do a slightly different area of science. Well, my kind of Bayesian filter says, I'm going to pay attention to what they're doing in that new area of science because I know they're competent and able to do things. Pay attention to what they're going to do. And but the systems of funding and so on, they don't really have a mechanism for that. If somebody starts a physicist and they decide to, real example actually, and then they decide to study hearing, for example, and from a sort of biological point of view, and it's like, well, you're a physicist, but over here we've got all these biologists who are being funded to study hearing, and you're not one of them, and you're not doing it the way that they want to do it, and so forget it. And I think that this, if I were thinking about the funding of things, I would bet more on people. I mean, you talk to sort of people in venture capital, for example, and they'll say that's what they are betting on in companies, but it's not how it works in science most of the time. In science, it's like if you do a different thing, but you're the same person, it's like, well, that's a different thing, and that has a whole different ecosystem for funding it, and so on. And I found it amusing. The only way I can describe it is that, particularly back in the NKS book days, people, well, a certain, for example, in the physics community, I think it was fair to say I was a very respectable physicist back when I was doing that stuff. And I think it was sort of amusing to me to see people say, well, yes, respectable physics. And by the way, we use, the software tools, he's built every day. But, well, the science stuff, that must all be nonsense. And I thought that was a very strange kind of Bayesian inference type conclusion, because it's like, okay, it's possible. I mean, look, I certainly would be early to admit my faults. I mean, like, for example, I did some science. I wrote a blog post about communicating sort of communicating ideas kind of across civilizations, so to speak, and can we put out beacons in the solar system that could be found by the putative extraterrestrial intelligence to know how great our civilization was? Okay, so I wrote that blog post, and I realized this is a pretty cool setup for some science fiction. So I sent it to some friends of mine who are science fiction writers, and one of them was like, wrote back and said, I have this idea for a story based on this. And I'm like, that's an interesting idea, but I think I have an even better idea. So I'm going to sit down for an evening. I'm going to write a science fiction story. And I realized I hadn't written a fiction story since I was like probably 11 years old. And I wrote this thing that, I think of myself as a decent writer and all that. And I, know a certain amount about people, so I can sort of put people into it. Anyway, so I send this story off to these friends of mine who are science fiction writers. And I think they correctly said, don't write fiction, stick to other stuff. So, I wouldn't advertise my my achievements there, although it's I think I would argue the ideas weren't bad, probably the execution was poor. Okay, let's see. Somebody's noting that when Newton was in quarantine, he invented gravity. Yeah, it's a good story. I need to look up that story in more detail. In 1665, there was a plague, bubonic plague, I guess, that affected all of England, and Cambridge University closed down, and Isaac Newton went to his kind of family home in Lincolnshire, and at least it is said that the very apple tree from which the apple fell, that from which he started thinking about his theory of universal theory of gravity, was there. I actually need to check into that story a bit more. I don't know all the details of it. I know only one piece of utter ridiculous trivia, which is that Newton, when Newton went to kindergarten, was a church school at a local church, which happens to be a church of Saint Wolfram, of all strange things. And I saw this in some biography of Newton years ago. It's Wolfram, actually spelled W-U, et cetera, et cetera, et cetera. And I was like, that's really cool. I never knew there even was a Saint Wolfram. There's a very minor saint, I have to say. But I thought that's an amusing piece of utter trivia of interest to me, if not to anybody else. Okay, I think we need to wrap up here. And gosh, so many interesting questions. Okay, somebody's saying they would rather go on with working sessions. Yeah, I should do that. That's what I'm really motivated to do. This is like fun for me, but okay, what am I? I'm being told to comment on the other live streams that we will be doing this week. Tomorrow we're going to be doing one that I'm really looking forward to, about connections with the distributed computing. And I think there's going to be some very fertile ideas to talk about the relations between what we're doing in physics and ideas in distributed computing. Then the next day we get to work on quantum spin and charge again. I've had an idea. We'll see whether that idea pans out. Maybe Jonathan and others will have had ideas as well by that time. it's yeah, looking forward to that. One of these live streams, we're going to crack what angular momentum really is, and then let's see, because I've been wanting to kind of do a bit of a public service, particularly during these pandemic times, to provide some material for kids who are stuck out of school. I am going to be doing another science and technology Q&A for kids on Friday. Actually, those have been really fun, and I might do them even when we don't have a pandemic going on. It's fascinating for me to try and take questions that and try and see if I can kind of boil them down to talk about answers without using a big stack of knowledge that that people would need to have. But anyway, so we're going another one of those about science and technology. So I'm kind of expecting both questions about how electrons work and how the internet works at that time. All right. Well, we should wrap up here. And thanks for joining me. Lots of really interesting questions, caused me to think about a lot of things. So I really appreciate that, and look forward to seeing you all again on another live stream in the future. Okay, thanks a lot. Bye.